hidden Markov chains on big data in order to predict where crime will happen at the city scale. Well, not globally at the city scale, but very precisely the different location where you can find a risk of crime. And the platform is actually used on site inside some police cars in order to prevent crime from happening. Okay, so there are a lot of discussion about this, whether it is prediction or verification of, because if you send a police car where you get a risk, probably you can avoid the risk, or there was no risk actually. But actually dealing with our project on agent-based simulation for crime anticipation rather, the idea was not really to predict crime from happening. It was more the idea of having a tool that enabled police to think about and to establish different strategies in order to manage different scenarios they got in mind. Okay, so dealing, for instance, with Montpellier, they observe quite recent tendency of crime coming from the Eastern Europe, and they want to have a tool that enables to explore different possibilities and to see how they could react to such a threat and how they could manage such a situation. So we are not really in the same situations than Predpol. And well, so I told this, and yeah, everything else. So we started with basic data analysis, just to tell that the data sources we get access to came from the police. So it is really the data that are entered into the system by the policemen themselves after some crime or some operation. During when they come back to the police station, they are entering all the information about the observed crime, and we got access to all this information. So it was there was mainly 3 components, and we used only the first one, dealing with suspects. So you get a whole data set about the suspects that are reported by the policemen. You get data concerning the different infractions that are observed by policemen, and data about victims. But we only use the first one. One of the trouble with such data, and when I talk about suspects, I'm not sure I have exactly the right term in English, but I'm quite sure I don't have the right term in French either, because the vocabulary related to police and justice is quite complicated. So it is a bit approximative, but you will get the idea probably. So one of the limits dealing with the data we actually got about the city of Montpellier is that the data are gathered by the police, but it can be corrected hereafter by the justice. So you get a clear distinction in between the 2 components, police and justice. And when you get a judgment, the judge can tell the police to delete every data about the people who is convinced or who is not guilty, actually. When you're not guilty, your data are erased. And at the same time, police need those basic statistics about what they do observe on the field, what they are. So they are gathering, they are still recording or keeping track of aggregated data from day to day, but dealing with individual cases, they only got the data corresponding to, let's say, people waiting for the judgment or people who are guilty. So it is a strong bias in the data. Another bias that we got in the data, if you look at the evolution of the number of infractions on Montpellier there, so the scale is not, you don't start from zero in in 2007, of course, but you get this kind of shape with, well, you can interpret it in many ways. There it corresponds to the death of Georges Frêche, who was an actual politician local politician in Montpellier, but probably there is no link with a decrease in crime, in criminality. There it is also the arrival of Sarkozy as president, but probably there is no link either with a decrease in criminality. More probably there was a change of the indicators concerning the actually crimes. And along the period of 10 years that on which we obtained the data, there were several changes in the indicators. So those data are not, as these are raw data, they are not so much easy to use. Okay. So usually the police service got an internal statistical service in charge of working on statistic and analysis of those data, and they correct everything, but we didn't access to those corrected data. So we got the raw data, that's all. But some of them were actually quite operational, and we could integrate it, as for instance, this one dealing with the distribution of the age of suspects. And it is quite robust, let's say, as a data. Okay. Last element with the actual model or actual project, we focused only on robbery. Why this? Because we didn't want to build a model or to integrate into the model everything that corresponds to organized crime with this is a case of drug, for instance, or car robbery. So there it is really, let's say, an opportunistic robbery cases. That's still quite a lot of cases, but it is more simple and individually oriented, more or less. Okay. So what we did after this is also to gather, because from the data we got, there was quite rich, they were quite rich, and we got the location of actual suspects, their location in terms of where they actually live. And well, a long time we got this evolution of the basic map of Montpellier that Kevin will probably recognize. I am not able really to situate myself there. Probably you got the city center over there. Concerning the feedback of the local police, they actually observe the same kind of thing. With some places, some locations that are actually that have a high concentration of suspects, and some others that move a long time during even during the 3 years period there. They observe the emergence, more or less, of some new location for criminals, let's say. Something else that we did is actually, because we got access to the infraction and we got access to which suspects appear on which infraction, and dealing with some infraction, we got several people that are actually linked to those infractions. So working on the co-participation to infraction, we were able to rebuild this kind of social network of people that are related to a different infraction. And well, basically what we did is a quick community analysis. That's why you got many colors there on Gephi. You got probably people who know Gephi, you recognize the layout. And what came out from this quick analysis was that there was a kind of an influence of the distance factor. People who are grouped have tendency to live together or to get close by, let's say. And you get an age influence. So more or less inside the same community, you got people who got the same age. Okay. And those are basic results that we used in order to regenerate the corresponding social network on the model. So in order to build the agent-based model, so we choose Gama because there was quite, and it was the occasion also to test this platform for me. And Olivier knows the platform, so it was better. And so even if we didn't use all the fantastic features that Alexis just showed us, well, it was convenient mainly because it integrates well all the spatial data and stuff. So we use it this way. And well, first bricks that we had to do in order to build our model was to regenerate a synthetic population. So for the rough idea, the population of Montpellier is actually 500,000 people. And well, even if probably Gama can stand 500,000 agents, it was more convenient to get a smaller population. So we decided to bias this population generation and to focus on 10% of the population. The idea, the rationale behind this hypothesis was to focus on the potential suspects, potential offenders in the population. And talking with the police, if you get more or less 10% people who are offenders in the population, it is a nightmare. So it corresponds to the worst case. If everybody in the population starts to commit crimes, well, it is not even Chicago, it is even worse, okay? So it was, the population generated corresponds to a worst case of potential offenders, okay? And in order to generate this population, then we can use the data communicated by the police. So we can use the distribution of age of not the real distribution of age of Montpellier, but the distribution of age of potential suspects. We can use their location, the way where they live, and we can use basically all the data the police got about the suspects. Okay, so that's what we did apply in order to generate our population. So dealing with the location, we use the data from the police, the age as well, and dealing with the social networks that we generate. We applied a kind of ad hoc model built quickly in order to take into account those two results concerning the age proximity in the communities and the distance factor, meaning that people who live together at the same place got the tendency to know each other. Okay, so playing with probabilities, mixing everything, we obtain this kind of network. So it is not so good, but well, it was a short project at the same time. And what we did propose was a kind of, not really a model, but rather behavioral model architecture composed with 3 layers that are activated the one upon the other. So you start, if you consider one agent, you start by computing moral values. So each agent got a moral value that can be encoded nearly as you want. So for the example, we coded it in between -1 and 1, and it corresponds to how people are considering crime, basically, whether they are totally opposed to crime or maybe they can consider it as a solution for their own living or whatever. Okay, so this is your moral judgment concerning crime in general. Okay, and if the agent is rather positive concerning the crime or they consider it as a potential way of living. They start a risk evaluation. A risk evaluation is a kind of evaluation of what you risk if you get caught committing an infraction. So it integrates at the same time the number of years of jail you risk when you committed a crime, and the kind of probability of getting caught if you commit a crime. Okay, so basically this risk evaluation integrates a kind of for the probability of getting caught, a local sampling from the social networks. So yeah, I observe my social networks and I got the knowledge about who committed crime and whether they get caught by the police or not. Okay.
You have 2 minutes remaining, Frederic.
Okay, or yet. And the last one is the choice of the modality. So if you the risk is positive, you accept to take the risk and you choose where to commit your crime. So on the city, according to a kind of origin destination matrix that put a correspondence in between your origin cell and the destination cell, you get a kind of attraction of some places, and according to this, you choose where to commit crime. So this was not really supported by theory. The idea with this architecture was to be able to generate a broad case of scenarios. Okay, the police got in mind really different scenarios concerning the ways they are managing resources, eventually new attractiveness at the city scale, eventually how to use social workers in order to influence moral values, stuff like this. So the architecture proposed have to be able to take into account this large game of scenarios. And dealing with scenario exploration, so you get some examples there. I will quickly do it this one. First one concerns the resources for the police. So according to a base scenario, we can verify there that the more police you got, the less crime you got. So the platform is working correctly. We could check also that local intervention, if the police choose to intervene, for instance, to put massive forces in the city center, the crime is not diminishing at the city scale level. The crime is just moving, okay, to places where you don't have police. And that's what they do observe as well. We were able also to simulate the scenario of the new stadium in Montpellier. New stadium means you get an attractive place because you got more people there and probably more steals to steal. And as an example for alternative scenarios, we get these scenarios for the support of juvenile offenders by social workers. So playing really on the moral values and the ways they can be taken into account in the platform. So more or less as a conclusion, the idea with such a platform was to evaluate whether it was interesting or not to use agent-based simulation in this context for the police in order to develop strategies for the management of criminality. And the feedback from the police was quite positive. And the potential of the architecture to simulate a broad range of scenarios, okay? And more or less it was the case, because in the different scenarios that were interesting for the police, we managed more or less to take them into account and to implement them into the platform. So it was quite nice. The bad aspects are probably linked with the data we manipulated, where we need to correct them or to obtain more valid data, more robust data. And well, that's it for the model, and I will be happy to take question probably at the end of the session.
Yes.
That's it.
Yes, will be the case. Okay, thank you very much, Frederic, for this presentation.
I didn't save time, basically.
Yeah, we ran out of time as usual.
Sorry.
So we'll switch quite rapidly to the second presenters, who is Mireia Jurita, if I pronounce it correctly. Are you there? Yeah, Mireia. Okay,
Yes.
so you will be talking about housing and mobility behavior, so related to urban dynamics. So it is a refined version of the scaling segregation model in Boston, if I understand correctly. So you have 10 minutes.
Okay, thank you, Kevin. So, well, hello, everyone. Today I'll be talking about how we modeled citizens' behavioral patterns towards housing and mobility mode for algorithmic urban policy design. So this is a project I developed as part of the City Science group at MIT Media Lab, where I was a visiting student there, along with all the people you see on the screen. So the presentation I prepared for today is structured as follows. So first of all, I'll talk about the framework, the goal of the research, and how we used agent-based simulations to model these behavioral patterns. So I'll give details regarding environmental variables, the agents, the process overview, and the calibration process, and finish the presentation, with some conclusions. So Cityscope was already introduced before, but well, some of you might already know it. Cityscope is a data-driven tangible platform that, aims at bringing different stakeholders together to collaboratively decide which are the most adequate urban decisions or the most adequate urban actions to be taken. So thanks to the feedback system, which is real time, it's very easy, or it's easier to bring experts and non-experts such as industry partners, people from academia, citizens, and so forth, around this table so that they can manipulate the Lego bricks and see real time how these urban disruptions would impact the urban indicators that form the Cityscope radar. So this is the Cityscope radar that tries to maximize 4 different parameters. These are density, diversity, proximity, and energy performance of cities or communities, so that we can boost social performance while minimizing the CO2 generation in those districts or cities. So this is, let's say, the broad framework of the Cityscope line of research. And as part of this Cityscope line of research, I started working on the algorithmic zoning project. So the idea behind the algorithmic zoning project is that developers could be given increased floor area ratios, that is to say, increased air rights in exchange for community amenities. So community amenities could include safe bike infrastructure, housing synchronization with jobs, grocery stores, and so forth. So this is a very broad research question, and I'll be focusing on the deficiency of affordable housing in city centers. So the vision of the City Science group is that everyone should have the opportunity to work and live within a 20-minute walking distance, so that big cities can be made up of autonomous communities where everyone can find everything they need for a living within this 1 kilometer radius or 20-minute walking distance from their doorstep. So the idea is to create a dynamic urban policy system so that we can reach this kind of vision of the City Science group. Okay, so the structure we came up with when we started thinking about this algorithmic zoning project is that agent-based simulations could be very useful to depict, to identify how people choose their housing options and consequently their mobility mode options. And these agent-based simulations could then inform of the consequences that incentives or urban policies could have on people's behaviors, so that these dynamic incentives policies could promote the pro-social cities, or these 20-minute cities that are becoming pretty popular in cities like Paris or Melbourne. These dynamic incentive policies could promote this vision of having autonomous communities within big cities. So the development of such a dynamic incentive system could be, let's say, classified in 3 main steps. I'll be focusing on this presentation on the first step, which is the study of the current situation. That is to say, the identification and characterization of people's behavioral patterns towards housing and as a consequence of their mobility mode. And this could be the first step towards the evaluation of of the consequences of static urban policies, so that this can then be used to create and design the dynamic urban policy system, powered by artificial intelligence. So the goal in one sentence would be to enable the real-time dynamic suggestion of housing-related urban policies that will contribute to an open, cross-sectoral and informed decision-making, that's Cityscope, let's say, while promoting greener, more walkable and diverse urban areas. That's the pro-social cities I was talking about. So the first step would be, as I mentioned, the characterization of citizens' preferences towards housing and mobility mode, and that's where agent-based modeling was considered to be very helpful. So when it comes to the agent-based model we designed itself, the environmental variables we used when it comes to geolocating the housing options were census block groups and buildings. So you're seeing on the screen is Kendall Square. So Kendall Square is, as you mentioned, it's located in Cambridge, in US, just next to Boston, and it's the area where the MIT campus is located. And the housing options would be geolocated using buildings in this area, in this 1 kilometer by 1 kilometer area surrounding the square. But in order to be able to work with a reasonable amount of environmental variables while representing the dynamics and the interconnection with the surrounding areas, so that people who work in Kendall can also choose to live outside Kendall if their preference score is maximized there. Those surrounding areas were represented using census block groups. So the agents that were making the decisions were people agents classified based on their income profiles. So the process is heavily reliable. It's based on the Schelling segregation model. So in each iteration, we've got a people agent based on their, classified based on their income profile, who can choose an alternative housing option B and compare it to current option A based on price, diversity, zone preference, and the commuting time. So of course, the commuting time depends on the availability of transportation, both private or public transportation in the area. So it's a joint choice model between housing and mobility mode. And these mobility modes would be evaluated based on time, the commuting price, the social pattern, and the difficulty of usage. So at the end of each iteration for each agent, we would have score A and score B. And the one that maximizes would be the one chosen by this agent. So of course, this process converges whenever the amount of people willing to move elsewhere approaches 0. So we try to find the weights the weights of these parameters that make the current situation be shown on this baseline case. And in order to do that, we define the mobility error based on the parking and transportation demand management data of the city of Cambridge, and a housing error using transportation and census data, and try to minimize, exploring these parameters, try to minimize the root mean square error of the mobility and housing errors using the definition on the screen. And that's how we try to find the combination of parameters that leads to this baseline scenario, so that once these parameters are identified, we can foresee how people would react to, say, static incentives, urban policies, and so forth. So that's the general framework I wanted to talk about. So we know that the calibration process, for example, which was held using the hill climbing algorithm, heavily relies on the selected starting point, and that alternative algorithms should be tested. So I think this plugin of OpenMol could be super exciting to try. But well, in general, we would say that we suggested a generic methodology where citizens' criteria towards housing and mobility choices have been defined. Could be fine or great, of course, but there's always this trade-off on Cityscope between the computational cost and the computation time, let's say, and the accuracy of the results. But well, we developed a model that would enable to predict citizens' response to housing-related urban disruptions as part of the Cityscope platform. So just very shortly, I would say that, well, we also try to use surrogate models that could make real-time simulations out of these, let's say, computationally expensive processes. Today, I was more interested in talking about the concept itself more than this, but well, if anyone has any questions regarding this matter, I'm more than open to answer them as well. So thanks.
Thank you very much. Right in time. So again, if you have any question, you can go to the Slack channel, dedicated Slack channel on urban dynamics, and you can have your question also in a chat right away. So we'll have the last presentation of the session. Thank you very much, Maria. It is Guilherme, if I pronounced it right. And we will travel again in South America this time for a model of the impact of increased sea level on residential choice and real estate markets, so in South Brazil. I let you start if you are ready, Guilherme.
Yeah, I'm ready.
Okay.
Can you hear me?
Thank you very much. You have 10 minutes.
Okay. So, hi everyone. My name is Guilherme Dalcin. I'm a master's student in urban planning at a university in South Brazil. And I will briefly present a model we have been developing using Gama for one of the researchers of our lab. So, the goal of this research is to anticipate future urban development trends for a set of coastal cities located in South Brazil, which have been presenting significant population growth. This population growth is occurring in a narrow land strip, kind of squeezed between the Atlantic Ocean and the region's set of lakes. So there's not much space to grow there, but the people keep on coming. And the impact of this urban growth is intensified by the arrival of tourists to the region's beaches during summer, which, as we can see in the chart here, almost doubles the population in the area during that time when compared to the rest of the year. And also, all this is happening in a region that is strongly affected by natural phenomena such as storms and floods, and that in the future will probably be impacted by sea level rise. So this map here shows that some portions of the region's urban areas will probably be below sea level by the end of the century. So this relation between urban growth and sea level rise becomes an interest topic for urban planning researchers to analyze. And we made a model, so in order to understand how the region will develop into the future, how it will be affected by sea level rise. And in this model, we're trying to model the process of people settling in somewhere in the city and the changes that this process causes in the urban environment. So with this, we hope to simulate the region's urban growth for the coming decades. And basically, in our algorithm, we're using a Gama species representing the population agents and the grid species representing the environment, which is coupled to two auxiliary layers that are used to compute attractiveness and land value of the grid cells. So basically, the population agents, they analyze the grid cells, they look for somewhere to settle in. And itself, this grid contains data on existing buildings and other kinds of existing elements. So the agent looks for a cell with available build space for him to live. And in the background of this grid, we use a graph representation of the cells and its connections so that we can use network analysis metrics to estimate the attractiveness of each cell. And these network metrics, they enable to differentiate cells according to the accessibility and centrality of the position of the cell in the whole graph. So the agent he analyzes these metrics in order to search for the most attractive cell he can find where he can settle in. And because all agents in the model want to settle in the most attractive cells, there is a competition for the available spaces in these cells. And this competition results in the land value of these attractive cells increasing as more agents are interested in them. And because the agents have different incomes, they can only settle in cells they can afford. So the pricing of the cells makes them occupy different parts of the environment according to their income. And since everyone wants to be in the attractive areas, from time to time we simulate that a real estate developer constructs more buildings in those attractive areas in order to create more space for agents to settle in there. And while all this craziness is happening, we simulate sea level rising, which blocks some cells from being occupied by agents, and also makes the agents that used to live there on those cells look for another place in the system, like completely changing the configuration of the system. So I brought some GIF animations of how the model looks like when simulated in Gama. On the left, we have the map showing how agents are distributed in the environment, where yellow cells represent residential agents and red cells represent commercial agents. The darker the color of the cell, the more agents are located in there. And in this map, we can see that during summer, the area gets a lot more crowded due to the presence of tourists, as it was said before. And on the right, there is the built area map, where the darker the color, the higher the building that is located in there. And this built area represents the capacity of the cell to host agents. And as it was said before, the most attractive areas receive more buildings in order to satisfy the agent's demand. And we also simulate here on the right the land value of each cell, and which is the expected price that each agent must kind of pay in order to settle in the cell. And we can see that it changes over time, but generally the higher values are located in the places where there are more people, so there are more competition. And these prices also tend to go way up high when tourists arrive during summer. We also keep an eye on the map representing the attractiveness metrics, which are computed using network analysis methods. And this one here represents a version of the accessibility metric, where we compute for each cell its average distance to places of interest, such as hospitals, schools, green areas, commercial buildings. And comparing both maps, we can see that the most crowded places tend to be also the most attractive ones. And finally, the sea level rise simulation is still being developed, but our idea is that the risk of flooding, which is represented by the blue color in the map on the right, would gradually grow according to the predictions for the study area. And this increasing risk would also gradually scare agents and make them move somewhere else. But right now, it kind of doesn't make so much difference in our simulations. And we're still in the process of calibrating and improving the model. So we still have not drawn any relevant conclusions from the simulations, but the animations we have already made are very interesting to see in the point of view of urban planning, and show that there is stuff that we can make with this. And giving some feedback about using Gama, we chose to use it because of its GIS data support and because of how easy it is to generate visual representations and charts. And the only problem we ever had is with the save simulation command that we have seen in the online documentation, but we never really could make it work but that's just a detail, and maybe even the problem is with us and not with the online documentation. So that was it, and thank you very much.
Thank you very much, Guilherme. Right on time again. So we will have 10 to 15 minutes for questions. And the last one actually from Guilherme is a question from the presenter to developers. So maybe you can have discussions about it in the Slack. So there's several questions from Patrick in the channel. The last one was for Mireia, and it was about the traffic jam, and if you take it into account for people to assess the commuting time.
So the commuting time in this case is calculated based on the available mobility modes, but as it was already pretty computationally intensive, let's say, we didn't take into account the traffic jams that this could lead to based on whether it is a rush hour or not, or this kind of parameters, for the sake of simplicity.
Okay. So there's no question in the chat, so I can go for, I have several questions actually, and there is one maybe related to jam and things like this. It's for Guilherme, and it's about the network that you use for assessing attractiveness of places. So what is this network? Is it a roads network? Do it takes into account the time for traveling and so on, or jams, for example?
No, we kind of define like a cost of moving between cells, like an impedance, and we execute some shortest path algorithms to find the shortest path between them. But the cost of moving between cells, it is like we hard code it. We define according to the size of the roads that exist in that intersect each cell, and we hard code it in the model.
Okay. Thank you very much. So I have also a question for Frédéric, the very first presentation we had. So you talked about the data that policeman gives you, but what about doing some modeling or even simulation exploration with policemen in order to have, I don't know, to validate hypotheses in the model or to have new insight, etc. Do you have any thought about this?
To make participatory modeling to build some model
yes,
all
sort
together.
of to have more data, to have more insight for modeling.
Yeah, it is a possibility actually. It is quite difficult because the police structure is quite rigid, and if you want to have people around the table in order to model, you have to ask the authorization to his superior and the superior of his superior, and so on and so forth. So it is difficult to organize, but still there are some people who got the competency at the same time to understand data, understand modeling, and also the willingness to do so. So it is a possibility. Due to the short time constraint for the project, we chose another option.
Okay. So there's one general question from Alexis, and it was more or less one question I have for all the panelists there. It was about connecting your models with deciders, and because all of them are related to policy design, to urban planning, and so on. So do you have any insight on the missing link, as Alexis said, to base the decision on your simulation and simulation results?
Well, in the case of our model, and I would say that Cityscope in general, it's like the first step to open up the debate, not only to experts, but only to non-experts. But of course, some of the calculations are simplified so that the results are displayed real time. And this would be just the first step to open up the debate, to discuss, to see what direction to take. But we would need to have further investigation or research into more specific urban policies afterwards. So it's just the first step.
I suppose for police, well, we are in the situation that is quite common, at least in France. I don't know if in other countries where decision makers actually know nothing about modeling or have little culture about modeling and the precaution you have to make when you're manipulating models. So it is quite difficult in this sense. But we will talk about this in the roundtable tomorrow, concerning the trust in models. That's a general issue.
Okay. If there's no more questions, so maybe we can have a small break, I think. Yeah, we have a 10-minute break in oh, we have remaining time to discuss a little bit, so maybe we can I can have more questions because I have more of this, and maybe another one for Mireia, because I was a little bit surprised because Cityscope is really into that kind of participatory thing, and you seems there to use calibration. So why don't you ask people directly to make the choose for living or to grow this data from people? You mentioned yes.
Yeah, that has already been done. So the model we developed is based on two main previous projects in the city science group. So one of them was developed by Arnaud Grignard, and that one was only focusing on the mobility mode option, and they did just that. Okay, how would you weight this parameter, or how important is this parameter when you're trying to decide which mobility mode to choose? That was before the pandemic, when workshops were possible. So in this case, I started with the project before the pandemic, but then the pandemic came. So that's the decision I made. Of course, the data is also from a moment before the pandemic, so it would be also interesting to see how this has probably changed.
Okay, thank you very much for the answer. So a few minutes remaining. If you have any question, I have still some of them. Maybe a last one for Guilherme. So what about the estimation of sea rising? So it was the very last part of your presentation. And do you have several scenarios to assess sea rising in your model? And how do you assess those scenarios based on models, or I don't know?
Yeah, we actually use data from an online platform called Coastal Risk Screening Tool from Climate Central. And from the data of that platform, you can get like 3 kind of scenarios: like the sea rise, the level of the sea by each year, the sea plus an annual fluid, and sea plus moderate fluid. So yeah, we're just working with the scenarios they provide.
Okay, thank you very much. And maybe a last question for me. I have plenty of those, as you can see. It's for Frédéric, maybe. So if I understood correctly, in your model, police impact on crime is indirect, meaning that people are less willing to commit crime when they see policemen in the area or things like this. And what about another source of lowering the criminality, like social workers or things like this? Do you plan to work on those kind of impact on criminality?
Actually, this is one of the scenarios that was designed by the police using social workers or the civil society more broadly in order to anticipate, let's say, criminality or fight against criminality. And we took it into account playing on the social network, basically introducing new agents that are social workers, that are connected to potential criminals, and that are trying to influence their moral judgments, moral values. So, well, I don't know, I am not sure, but the model is still, a bit rough to say, but it can take into account such cases and such scenarios.
Okay, nice. Thank you very much, all of you. It's time to have a break, I think, and thank you again for your very nice presentations.
start again, following strictly the schedule imposed by Patrick on the program. So this is a session on social dynamics, the first session on social dynamics. So as usual, not as usual, we'll have 3 presentations, 2 long and 1 short. As usual, the question will be put at the end of the session. And in the meantime, you can write your question on the Slack channel that is called Social Dynamics, just like the session. And well, first presenter is Aya Badawi. Aya, you're ready?
Yeah, how are you?
Fine, thank you. And you got 20 minutes to present your research. So the ground is yours. Perfect.
Hello, everyone. So my name is Aya, and I'm a PhD student in University of Manchester, and this is my 3rd year of the PhD. So in 20 minutes, I'm going to introduce you to Your Plans. This is an urban planning negotiation simulator that we developed in Gama. So what to expect from my presentation. So if you are listening to me and you're a Gama developer, after the 20 minutes, you can expect to hear some feedback about using the features and the different capabilities of Gama, and also some ideas about future collaboration and about future enhancement that could be integrated in Gama. If the listener is an urban researcher, you would expect to have an idea about an important area of research in urban planning that really needs our support as researchers and academics. And if you are a general Gama user, not in urban planning, so you're going to know about the advantage of the BDI architecture compared to other architectures when simulating social dynamics. So let's start. So what was the motivation behind the Your Plans simulator? So at first, when we observed the simulators of urban planning in general, we noticed that most of them simulate the spatial dynamics, like the urban growth, the transportation, the mobility, and so on, in order to support decision makers in taking decisions. But what they forgot is that actually, even after showing them these simulators, it is rarely that a decision maker can take a decision individually. Most of the time, he needs to sit with other decision makers and they need to reach an agreement to get to a group decision. They need to negotiate, and these negotiations are very challenging and they require a lot of skills. And unfortunately, we don't have any simulators, and there are like very, very few simulators, and they are all basic and they cannot be reused on other cases. So we do not have a support system for urban negotiations. And accordingly, we had this purpose that we want to develop an agent-based simulator that could simulate urban negotiations in order to support decision makers. What exactly the kind of support that we wanted to do? We wanted to help stakeholders to understand the impact of their behavior and skills on the outcome of negotiation. In other words, what happens when they change their behavior, not in terms that this predicts the outcome, but to give them a sense of, if you react this way, this will lead to the outcome to be that way. And if you were more, for example, flexible, or if you had a flexible agenda, you will be more likely to get a positive outcome. So this helps them to improve their skills and to understand how sensitive their behavior and their agendas may affect the outcome. We had 3 specific design objectives when we thought about designing the simulation framework. The first thing is for the framework to be reproducible. And this means that, as you know, negotiation could be very different and varied among places and contexts and different reasons for people to negotiate. So how could we develop a framework that could be applicable to many different cases of urban negotiation? So we wanted to be reproducible. The second thing we want the agent or the simulator to simulate complex exchange of offers. What exactly complexity did we want? We want agents to be able to suggest other solutions when they reach a deadlock in the negotiation. And this is not actually done in current simulators. So this is the area of complexity that we wanted to add. And the last thing, because as we said, this simulator is meant to be a support system, and we wanted to show it to stakeholders to get their feedback on it. So we wanted the simulator to be user-friendly. So how did we design it? So this is the conceptual design about it. So first, just to give you an idea, in negotiation in general, the process is that you have two things, strategies and tactics. Strategies is when you say, okay, I will react to the person I'm negotiating with by arguing or by modifying the numbers, for example. So conceding or argument is a strategy. A tactic is how you will implement this strategy. So if you say you will modify the value of your offer, the tactic means how much modification. Will you make a big modification or a smaller one? If you are going to argue, your tactic will be, will you try to convince the person in front of you, or will you try to threat and leave the negotiation? So this is the basic idea of the process of negotiation. Aren't there any negotiation simulators? Well, there are, but not in urban planning. As I said before, the ones existing were developed by artificial intelligence researchers and people from computer science. So why can't we use them, just take the simulation framework and use it in urban planning? Because they had like a very important or major problem. That is that when they simulated how people negotiate, they considered that, first of all, they didn't include the argumentation, which is okay because it's highly complex, but the real problem, so they simulated how people modify the values of their offers. And the problem is that they considered that agents only think about the value of the issue that they are talking about, which is called position-based negotiation. And this rarely happens in reality. Imagine, for example, you have this pen and you want to buy it and you're negotiating its price. So you're saying to the seller, okay, I will pay £3 for you. If he doesn't agree, you will say, okay, I can give you £4. What actually you're thinking about is not the price of the pen, but you're thinking about the relation between this price and the total money in your wallet. So there is like a base or an interest or a goal in the back of your head that when you think about the negotiation, you think about it and then you translate this into an offer. So is this a big problem? Yes, in urban planning it is, because if you think about land developers, a land developer think about the profit, not about the number of housing units or how much price will they pay or get from it. So they have to think or concede or apply the tactics in the mind on the profit, and then make this translation. And the profit equation is actually a bit complicated. So make this translation from the profit, okay, how much units will get me this profit, and then we'll make the offer. So this distinction between the interest and the position is very important, and it wasn't captured in the existing simulator. So the first step to do was to separate between the goal and the issue, and to let the people think about the tactics, or when they negotiate in terms of their goal, and then make a translation or translate how much of the issue will be complement to this goal that we want. The second thing that we wanted in our framework is, as I said, I want people to be able, or agents to be able to suggest other solutions to the problem. How can we do that? So we had first to understand what is an urban issue that they are negotiating on. Well, actually, in urban planning, the stakeholder has an urban activity that he wants to do it in order to achieve the goal. So if he's a land developer that he wants to achieve profit, the urban activity will be to develop a housing project, for example. The plan would be, I will develop a housing project in this location with this number of housing and this mix of the tenor. So the number of housing and the mix of the tenor are the issues that they negotiate on. If you have this idea about the structure of the urban negotiation, you can then imagine what would be the different issues that the agent can move on. So just imagine the urban activity and imagine the different plans that an agent can have. For example, by saying, okay, the plan is to develop the housing project once in this location, other time in this location, in that location. And so we will have the different issues, and then agents will then be able to pass from one issue to another and propose other solutions to the negotiation problem. So this is the simulation framework. How will we develop it in Gama? We need agents actually to understand that this is a plan and this is an activity. And if I want to suggest other solution, I need to move from this plan to that plan. So agents need to be cognitive. And to do so, we applied the BDI architecture in Gama, the belief, desire, intention. So I think there will be more details on the BDI architecture tomorrow, I think in one of the afternoon sessions. So I will not describe it now in details, but I will say quickly how we transformed this simulation framework into the BDI architecture. So the strategies turned into desires, tactics turned into plans. The major urban activities like developing a housing project became a desire. The plans by doing, okay, these are in this location with this number of housing and so on, so became plans for the desires. And agents have certain beliefs. These beliefs will be the criteria upon which they determine which plan here or which tactic to choose, and which plan also here to choose. Shall I suggest another solution or not? Each agent will have a belief in its mind, a certain criteria, whether it's the time, whether it's the behavior of the person in front of me, the conditions around me, my prior expectation, whatever you want to add as the criteria, you will add it as the belief, and the agent will use this belief in order each time to think about which tactic to use, and then when translating this into a proposal, which solution to propose to the opponent. And we use them to communicate with each other using the FIPA skill also in Gama. The last, if you remember, the third objective, we wanted to be user-friendly, so we used the gaming features in Gama, particularly the user input and the user control. With this like major simulation framework, we had an application. We applied it on a case of negotiations of developer contributions in England. So this is a case in which whenever a developer wants to develop a housing project, a private housing project, according to the law, these developers need to contribute a percent of this project as affordable housing in order to get the permission to implement this project. So we have three agents: the developer, the local planning authority, and after the developer negotiates with the local planning authority on the percent of affordable housing and the type of the affordable housing, he then goes to the housing association. This is like an organization in which the developer sells the affordable units, and this housing association rented to the people after that. So the developer negotiates with the housing association on the price of selling the units. As I said, the agents should have a criteria of determining which desire or which tactic to use and which solution, when to move from one solution to another. What is the belief or the criteria that I used? Well, I used the prior expectation. Whenever an agent, they start to negotiate, they should have at first a prior expectation of the outcome of their negotiations. And upon this expectation, they just determine how to react. How did they get this expectation? I coupled another model which I made before for the negotiation. It was based on the finite state machine, states and transition. And inside the model, agents run this first model, and then they get an expectation plotted in a curve, and accordingly, they try to react which tactic to use. I know that I think I have just 1 minute left, but I will show you the gaming features very quickly and some conclusions. So at first, when you open the model, you'll have this startup page. in which here you will enter the data or the parameters of the project, and here you will have how they will communicate together, and you will open the negotiation monitor. This is how which works along the negotiation, the path of the negotiation throughout the process. When you run it, okay, so ideally this should be for each stakeholder alone, should have his own version. Each stakeholder will have like a pop-up message. It's like a game telling him, okay, this is the condition now. Please enter your agenda or how you want to negotiate in this process. And we enter and so on for the planning authority. What is happening there? And then they run the first model in their mind quickly. The blue line is their expectation that they use. And this is how the offers is done. When they finish, they negotiate with the housing association, and another pop-up message saying, okay, this is the condition, please tell us your agenda. The same for the housing association until the negotiation ends. Because we use the belief, desire, intention, so we can add more explanation. If you hear stop at any of those negotiations, you'll have any of those charts will have more explanation about saying, okay, this is how the negotiation ended and why did it end. The same if you stand here. So people using the simulator can have more idea about what happened in this negotiation and why did it end and what was the problem, for example, if it failed. You can create another simulation and change your parameters, and then the simulator will also provide you with comparative charts between the different parameters that you added. So we showed this simulator last month to a group of stakeholders, and we had a lot of positive feedback in which they said that they could integrate it in their organizations, but it needs to have more capabilities and complexities, particularly the argumentation skills. So to conclude, if you are a Gama developer, I have 3 messages. The first thing is that I felt that Gama has better potential to be used for urban negotiation than other agent-oriented platforms like Jack and Jade, because it has a GIS capability, and also the capability to have charts and so on is very useful in urban negotiation. The second message, I think that if we improve the gaming features and the Gama web, your plans as a simulator actually can be developed into a serious game. So if Alexi was talking areas of support that we need to think about, I was thinking about the gaming features because it could bring the simulator to another level. The third message is that I knew that Patrick has already worked on the argumenting skill. And as we got feedback from the stakeholders that they need argumentation in the model, so how can we integrate the argumenting skill in your plans? If you are an urban researcher, 2 messages. Urban stakeholders really need support in urban negotiation, and that's what we got from the workshop. The second thing, we need to test this whole generic framework on other cases of urban negotiation. Lastly, if you are a Gama user, because I tried another of simulating negotiation on a finite state machine architecture, I can tell you using a cognitive architecture really differs. And this modularity helps you to get a lot of features and makes coding a lot easier and helps in the interpretability of your simulator. And finally, I'd like to thank the whole developer team of Gama, because I have been like sending a lot of emails and asking about a lot of things throughout the process, especially Patrick Thailandier. Thank you very much, and I hope you found those 23 minutes useful, and I will be interested to to hear about your feedback and comments. Thank you.
Thank you very much, Aya. A very interesting presentation and very, very good feedback for different public. So for those who get questions, just remember to ask them using the Slack channel dedicated to social dynamics. And now we can move to Loic, who is actually a former student of the team. So I'm very happy to introduce him. Loic, hope you get well, and you got 20 minutes for your presentation.
Okay. Let me share my screen. Okay. You have to set something.
You got 19 minutes.
Okay. I need to restart Zoom. I'm quick.
Maybe we can switch to the third presentation, and then when Loic will come back, well, oh, he is yet back. Loic, it is okay? And now you can share your screen and activate your mic. Yeah, that's good. We see everything. Don't forget to activate your microphone.
Okay.
So you got 15 minutes now.
Please no. Okay, I can get this. Do you see my screen?
Yeah.
Okay. Yeah. Okay. So, hello everyone. My name is Loic Sadou. I'm a first-year PhD student at INRAE Toulouse. I'm a PhD student in computer science, and I am supervised by Patrick Théandier and And today I'm going to introduce you to my recent works about innovation in behavior. But before getting deep in the subject, let's get some context. I talked to you about the Lot. It's a river in the south of France. And the region around the Lot suffers a silver drop during the summer season. That implies water problematic. And the local water institution proposes new communicating water meters to answer this problematic. And this is for the farmers, because there is the one who was the most impacted by those water problematic. Those new communicating water meters have some advantages. The most important one is the fact that they allow to have the water consumption in real time, and also they are more accurate than the old ones. But despite those advantages, the new communicating water meters are globally not well accepted by the farmers, especially because they are suspicious about where the data are going, and they are also afraid about the rise of the water bill, because the previous water meters were less accurate, and sometimes they display a lower value than it was the fact. So this context is an innovation a different case, because you can see the new communicating water meters as an innovation, and the potential adopters are the farmers. And what is innovation diffusion? It is a part of the social simulation field, and it's hard to talk about innovation diffusion without talking about Everett Rogers, who is an economist from the past century. I will not talk about all the works about Everett Rogers, but one of the main is the design of the adoption process. It's a 5-step process, will be followed by the potential adopters. The first step is it's a knowledge step. During the one, the potential adopters will be aware of the innovation, and will collect some information about it. After that, there is the persuasion step. During this step, the potential adopters will have an opinion about the innovation. The most crucial step is it's the decision step. During the one, the potential adopters will decide if they will adopt or not the innovation. And if they will adopt, they will go to the implementation step. It's the step during they will use the innovation. until they go to the confirmation step. This is a step where they will decide to continue to use the innovation or not. So that was the beginning of the innovation diffusion work. After that, there is some agent-based model that decided to use this paradigm for innovation diffusion. I put here some references. The first one is it's a classic model. I think Patrick knows it well. It's about the relative agreement model. It's a very classic, and it was one of the first model about the first agent-based model about innovation diffusion. I also put a review if you want to read it. There is a lot of agent-based model used in the case of innovation diffusion. Despite the fact that there is a lot of agent-based model used for innovation diffusion, most of those models use abstract values to represent the opinion about the innovation. And those abstract value doesn't provide much information about the agent's state of mind and what do they think about the innovation. So it makes it hard to understand the details of the diffusion process. And this is the problematic we want to answer by adding some details about the agent's knowledge. So we propose the model to answer this problematic. In our model, one agent is the representation of one individual, one potential adopter. And our model can be sliced in three main parts. The decision model, based on the theory of planned behavior, the agent knowledge representation using the argumentation theory, and finally, the agent's interaction inspired by the DMS dialog. So like I said, we use the theory of planned behavior. It's a pretty popular psychological theory. It is centered around the concept of intention. So originally, the intention is the intention to adopt a particular behavior, but in our case, we use it as the intention to adopt the innovation. So the intention is derived from three other concepts: the attitude, the subjective social norm, and the perceived behavioral control. So the attitude is the opinion and the knowledge the agents will have about the innovation. The subjective social norm is the agent's impression about what their relatives think about the innovation. And the perceived behavioral control is the ability to adopt. It can be seen as the ability in terms of money, in terms of time and skills too. Usually this last value is here to balance the two others. This theory is pretty abstract, so we had to build link between an agent-based model and this theory. So for the attitude, we managed to compute an attitude value using the arguments known by the agents. And the subjective social norm is a value updated during agents interaction. So I won't talk much about the perceived behavioral control because it's very related to the applications case. So I talk about arguments. What is arguments? There is many representation of argument in the literature. We choose the Doom's argumentation framework. This framework is centered around the concept of argument. It is the atomic element of this framework, and you can see it as a vertex of a directed graph. So the argument is a vertex. So we have the attack, which is the edges of this directed graph. So you can see here, we have the argument A attacking the argument B. And with the concept of attack, we also have the concept of defense. So like I said, the argument A attacks the argument B. And we have the argument C attacking the argument A. So the argument C is defending the argument B. So we have the concept of argument, attack, and defense. And from this, we can have extensions. So there is many definition of extensions. I put the preferred extension because this is the one we used in our model. So I will not get deep in the subject in the details of extension. The preferred extension allows us to get the arguments that are valid. That means they are not attacked by other arguments, or if they are attacked, they are defended by other argument in the extension. So we use it to extract a valid argument from a set of arguments. So with this framework still pretty abstract, and we need to extend it to use it in our model. For this, we added some attribute to the argument. We added an ID, an argument type. So this attribute allows us to know if the argument is in favor or against the innovation. There is also a statement, which is the definition of the argument, the justification of the statement. There is a criterion. No, it's hard to define, but it's a general concept of the argument. It can be an economic argument. It can be an ecological argument. It represents the side of the innovation. And there is also a source. This is where you can get this argument from. So don't worry, I put an example to illustrate what I just say. So here, this is an argument about the communicating water meters. So this is the first argument. You can see the type is a plus. So it's an argument in favor of the communicating water meters. The statement says that the new meters are more accurate. Why? Because they use the ultrasound technology. And this argument concerns the performance criterion. And where did I get this argument? I get it from CELLULAR. So I put CELLULAR, but I can put something else. I can put an advertisement. I can put this representation of arguments is the way we use to put the knowledge in the agents. But now they have to confront their argumentation graphs to revise their opinion about the innovation. And this is why we do with dialogue. So at each time step of the simulation, each agent will communicate with a relative. So we build a social network using a classic small word algorithm. During those interactions, the agents will update the subjective social norm related to the theory of plane behavior, like I explained earlier. But most interesting, there is a dialogue, a real dialogue, that can end up with a bilateral trade of arguments. That means that both agents during the interaction can lose or gain arguments. And also, we managed to implement epistemic vigilance. Quickly, this is the fact that the agents will not believe in everything they hear. So they don't get every argument they get from other agents. So this is important. To illustrate what a dialogue can be, this is a little example. So we have two agents with a different argumentation graph. The agent S will start the conversation by saying the argument B. The agent R will answer the argument B by saying B is not valid because I know an argument A attacking B. The agent S will say, I know an argument C attacking an argument A. And R will answer, E is attacking C, so C is not valid. And say the agent S, sorry, the agent S will answer, okay, because I don't know any argument attacking E, so I'll accept this argument, and I add it to my argumentation graph. And so you can see here the new graph of the agent S. I put in green the element of the preferred extension. So as you can see, the preferred extension of agent S have changed, and we computed the attitude from preferred extension. So the attitude of agent S will change during this dialogue. So this is how dialogue works. I just presented to you the main component of the model, and we decided to apply it on the communicating water meters in the region of the loop. For that, we had to extract 40 arguments from the literature, from website, and also interviews with the farmers of the region. And after that, we created 107 attacks to link those arguments in a global argumentation graph. We feed the model with 60 agents, which is the number of farmers in the region. And obviously, we implemented it on the Gama platform, which is very convenient using the argumentation plugin. So this is the first results we get. Those results show aggregated data about 100 simulation step. The x-axis on both graphs shows the simulation step, and for the top graph, the y-axis is the intention value, which is a value between -1 and +1. And for the bottom graph, this is the adoption rate, so it's a value between 0 and 1. As you can see, those values show a positive adoption and a very positive intention. As you can see, the mean intention for 100 simulation is around 0.5. What's interesting about those results, it's they are close to what we observed about the previous water meters, the mechanical one, not this one. So it can be seen as real results, but maybe we are far. Also, you can see that there is a big difference between the mean and max value. This is the blue values here. This can be explained by the argument, the distribution at the beginning of the simulation, because the distribution is totally random. Some of arguments doesn't be present at the beginning of the simulation. So maybe some arguments that are very important are not present during some simulation that can lead to extreme values for intention. So this is the classic scenario. We try to implement a new scenario by adding just one argument in the pool of the 40 others. As you can see, the blue curve is the classic scenario, and the red one is the scenario with the new argument. So you can see by adding only one strong argument, you can have a pretty strong impact on the blue curve. And this is what we want, because this is a strong argument added. That means that no argument attack this argument, and this argument attack many others. So from those graphs, you can say that the local institution that proposes water meters have to be very vigilant on those kind of arguments if they don't want to have a lower adoption rate. So to conclude quickly, this was the presentation of preliminary works on a generic model. We use it on the case of communicating water meters, but you can use it on various other themes. We have a priority on the data collecting, especially to build a better and more realistic farmers' psychological profile. And on the side of enhancement, we managed to better distribute the argument, because we distribute all the arguments at the beginning of the simulation. But some of the arguments can be obtained only by using the innovation. So it's not very current on this side. And finally, we wanted to implement non-interpersonal communication, like a website, like a TV or radio, because actually we have only a dyadic interaction between agents, which is not the ideal way of getting information on a particular subject. You can easily imagine that if a farmer wants some information, they directly go on Google and not necessarily speak with a neighbor. So I hope you enjoyed this presentation, and if you have questions, I'll be happy to answer it.
But not now.
Not now.
Not now. Thank you so much, Loïc. So if you have any question, you can use the Slack channel again, the social dynamics. And now we can leave the ground to Gamaliel, who is ready, and
yeah.
and you got
Thank you.
10 minutes to present your work.
Yeah, just a minute. Let me share
floor
my
is
screen.
yours. Sure. And it works. Wonderful.
Okay, you share my screen? You see my screen?
Yeah.
Okay. Okay, thank you. Yeah, hello. My name is Gamaliel Palomo, and I will present to you this work that we have been doing in collaboration with Arnaud at MIT Media Lab. We are Gamaliel Palomo, and I am a PhD student in computer science, working with Dr. Mario Siller at Simesta Guadalajara. The work is the relationship between the cultural orientation of a population and the evolution of an epidemic. This obviously an agent-based approach. Okay, yeah, first of all, a little bit context. In the 11th of March, the World Health Organization declared coronavirus disease a pandemic, as you know. And this disease is caused by the SARS-CoV-2 virus, and by June 22, there are more than 178 million confirmed cases of COVID-19. No? This is an updated data from the authorities for yesterday. Well, it is important to consider the effects that intervention for the mitigation of an epidemic will have on the population prior to its implementation. As you know, we have been implementing a lot of measures that are recommended by the authorities, by our governments, and that measures vary through washing our hands, social distancing, having some kind of behaviors, do not meet in groups of many people, some interventions like that. No, but it is important, seen from the social sciences, that we see that that measures in a way that we understand what are the effects of that interventions on the people, what can that interventions cause in people, what effects can be seen, and what are the responses by the people, by the population to that measures, and what that responses can generate to the dynamics of the epidemic. So that is a little bit the objective of this presentation. We studied the dual causality that has been the object of study of social and behavioral science, with the aim of helping to design better interventions that are adaptable to different types of population and giving a greater probability of success. Every population is different, so we need to think about different kind of interventions in order to address this pandemic and future pandemics. That is the objective. So for that reason, this work, we propose an agent-based model for the study of the dynamics of an epidemic, of course, taking into account the cultural orientation of that population. As I said, every population is different. Every population has a different cultural orientation. So this proposal is divided into three main submodels. First of them is a model of contagion and spread of the disease, a model of mobility, and a culture-based decision-making model. Okay, first of them, the model of contagion and spread of the disease. As the majority of you know, a model that we use is the compartmental modeling that is based on a series or a set of possible states or possible epidemiological states that an agent can be in. And this is not this is not an exception. We use an SEIR based model in order to represent the different states that that an agent can be. No? So we just add some states that are related to the behavior, and we separate them from the states that are related to the epidemiological states. And of course, we add some time periods that are the times that agents can be in a specific state. So people go from susceptible to exposed once an exposure to the virus has happened. Then that agent goes to an infected symptomatic or asymptomatic, and then goes to recovered or and immune or the agent dead. Yeah, that is the first submodel, the model of contagion and spread of the disease. The second submodel that we consider is a model of mobility, because we are interested in consider how the virus spread through the mobility, no, through a daily life of people. So we consider two kinds of activities that are the recreational and economic activities. For this, we use an agenda-based mobility submodel. So we consider a series of activities that people develop through a daily life. And yeah, each simulated day, an agent will plan a series of activities which will take place at a specific place and time. Once an agent finishes, he heads to a place designated as his home and do this day by day. The third submodel that we consider is the culture-based decision-making model that is based on also in the theory of planned behavior. In the literature, some works address the correlation between the cultural orientation of a population and the epidemiological behavior. In this first reference, they conduct an analysis of the COVID-19 data collected from 69 countries, and they found that people with an individualistic profile had a greater probability of not adhering epidemiological prevention measures. So people who have a profile, an individualistic profile, think about themselves, not about the group, not about the community. And people with a collectivistic profile tends to adhere more to the interventions or to the recommendations. So based on this, we made an implementation for our model using the TPB. So we know that adhering epidemiological prevention measures is a culture-based decision that people make. So this is based on a decision about using or not using the recommendations, wearing or not wearing the masks. So to model decisions, we use the theory of planned behavior, that is a social psychology theory that involves the beliefs and behaviors of individuals, which can be expressed through three components: the attitude towards behavior, subjective norms, and the perceived behavior control. But yeah, TPB has proven to be very useful, mainly to explain decision-making related to a large number of behaviors. Such, we put some examples like addictive behavior, eating behavior, and exercising behavior. But in the field of ABM, how can we implement this kind of decision-making models in in a very easy way. You know? So we base our work in a work presented by Hyun et al., where they use Bayesian inference, a mapping of Bayesian inference, and a cost loss model to implement decision making through TPV theory. This is how it looks. We have a probability to make a decision, and that probability is updated every time that agent needs to take another decision. So we have a decision at time t that is beta, and it is calculated based on a previous value at time t minus 1, and it depends also on a cultural orientation coefficient that we call delta, and a variable epsilon that represents the external information that comes to the agent that can be information about hospitalization, the contagion rates, how many people is infected right now, some kind of information that can affect the decision of that agent. We implemented this model, this three-sub model using the Gama platform. Yeah, the simulation scenarios are geographically located in the Lomas del Centinela polygon in the metropolitan area of Guadalajara. And we use for that geographically referenced data. And this is how it looks, our geographical user interface. But we made some assumptions. For example, a total of 180 days simulated. We also suppose that agents carry out a random number of daily activities following the decision making. Model explained in the previous section. It is assumed that disease has been imported by agents who returned to the community without taking precautionary measures. We initialize the parameters using 400 people agents for each population. The initial number of people exposed is 10. And we base the epidemiological parameters based on the results reported in the literature. And this is part of our results. We divided the experiments in two kinds of population: a balanced population, an individualistic population, and collectivistic population. Balance is a population where we have individualistic people and collectivistic people living in the same area. Collectivistic and individualistic are the extreme, the population that only cares about themselves, or the people that attend the recommendations. No, so we have some kind of results that help us to see that having a population made of collectivistic people results in a better addressing of the epidemic. So we can see for example, the basic reproduction number. During the simulations, we observe an average of 0.87 in the value of the reproduction number for the collectivistic population. That is, as you can see, very different from the balanced population and the individualistic population. Also,
sorry, Gamaliel, you should conclude now. You're far ahead of the time limit.
Thank you. Yeah. Only we can see the epidemiological indicators such as susceptible, exposed, immune disease people. But most important, in conclusion, as a summary, we can see that a population with collectivistic collectivist people will tend to respond in a better way than individualist or balanced people. So yeah, we can show with this kind of model and simulation that it is possible to model both contagious and diseases and social phenomena to study the associated emergence and the general effects on the evolution of an epidemic. And this would allow for more precise or better adjusted epidemic interventions according to the specific characteristics of a given model community.
Okay, thank you. You should have chosen a 20 minutes intervention and not a 10 minutes. Okay, so let's move to the question. If you got some, I got the first one for Loic, actually, dealing with argumentation. I was wondering, how do you obtain data actually for arguments? How you integrate it into your model, and where it come from globally, or do you do it by hand, or is there an automatic process?
To construct arguments, you mean?
Yeah. To get your 40 arguments you give at the end of your presentation.
Yeah, basically it's manually. You read papers, you read some websites, and you try to collect some arguments and to hide them all, most of them. Also, the attacks are created manually. There is an automatic way. We tried it. It doesn't provide very good results, so we need to create manually the attacks to have a more current global argumentation graph. If not, the results are not cool.
Okay. Is there any other question on Slack? Not so much. You got the question. Probably you can tell it loud. Still, Loic, dealing with what about the strengths of an argument? A question asked by Jonathan. Some arguments are more convincing than others. How you include it into your model?
Yeah, I should have a talk about it, but each agent have a set of coefficients that allow us to compute the strength, the value of an argument based on the criterion and the source of this argument. This is part of the psychological profile, like I said in the conclusion. So each agent have a particular way of computing the strength of an argument, and by using the criterion and the source. This is the way we managed to do it actually.
And the way you ponderate it, you do it by hand, basically.
We use some data about this coefficient from another paper, but it's a paper about the green agriculture, so it's not very convenient for this this model. It's just to feed the model to have preliminary results.
Okay, nearly the same question for Gamaliel, actually, dealing with the cultural parameter, your delta stuff. How do you find the value for this delta? Does it come out from your art, or?
No, yeah, actually, it is from some psychological research where some people have made some kind of field work where they determine what is the the cultural value of very specific populations. I showed a research that is made of 69 countries where they determine how individualistic is a population, and they deliver that results as a way of a value, and I take that as a delta value.
Okay. Maybe a more global question for the two first presentations, maybe Gamaliel, you got an opinion about this as well, but the two first presentations were more about, let's say, a kind of rational process for decision making. And I don't believe that individuals are purely irrational. So how you can hybridate such decision or bias such decision. For instance, in your case, Loic telling that, well, after an exchange or few arguments, well, people do not change anything and they keep their opinion. For instance, you cannot argue indefinitely with people. Or for Aya, this is the same with negotiation. You negotiate for 1 or 2 rounds, but after that, well, you're fed up and you just say, well, stop. So how you can start from a rational framework and try to introduce bias on this.
Yeah, actually, I added this. It's called in negotiation good enough, that it couldn't be like the best thing, but he just gave up and he can, okay, I will accept this and just leave. So this is like a terms of the suspense in the negotiation that and the uncertainty. So at first I added it like that if he calculates the expectation and he feels that the person in front of me is not giving me a lot of good decisions, and this has been in 2 successive rounds, so I will feel that I'm fed up and I will leave. And also there is a factor of randomness in the expectation. So after they calculate the expectation from their first model, I add a factor of randomness to account for any incomplete information. So if you look at the graph, you'll feel that the line is going upwards and downwards a bit, because even after they calculated the expectation, this might change a bit randomly as they get more information during the negotiation. So there is a bit of stochasticity in the model, but in a very small amount.
Okay, good answer. Yes, thank you.
Yeah, in my case, there is sometimes that the dialogue will end on not okay, and none of the participants will acquire some arguments. They just don't agree. They are too far. Their opinion are too far, so they just talk, try to be convincing, but this will lead nowhere. So they end up like this, and yeah. One of the ways is the perceived behavioral control that allows the fact that even if I have a good intention to adopt, even if my social network want to adopt too, I won't adopt because I don't know, maybe I'm lazy or I don't have time, and it is the way you can put some bias in the model. This is the yeah.
Okay, thank you.
That is the way.
I can also believe that you have in the BDI architecture the emotions and the social relations, and also if these factors are added, we could have this more bias and have this personal things and personal feelings when people either argue or negotiate. So I think the BDI architecture has a lot of good features that could add this personal thing.
Yeah, moreover, you get an emotion extension on Gama, so you can, but you have still to articulate it together with the BDI extension, so it is not probably not so easy. But do we get time for a last question? Yeah, maybe just concerning Loic and Gamaliel. Actually, you take as a ground, as a basis, the theory of planned behavior. And you came up with quite different implementation, because Gamaliel, you got this huge formula that is use function, and Loic, you implemented a more BDI version of the theory. Do you have a feedback to share concerning the work of the other, or?
I don't understand. Sorry. What?
Well, you implemented a kind, or you used the theory of planned behavior.
Yes.
just like Gamaliel just after, and your implementation choice is radically different because Gamaliel obtained this kind of functional form for the theory of planned behavior, and you probably preferred a kind of BDI option. And so I was wondering, why is there one form that is better than the other? What do you think about this?
I think the way we started to use it, it's to implement argumentation. It's one of the a big part of the this model. So using argumentation with an economic function is a bit awkward because it allows a more BDI side. Good question.
Yeah, I think that we have to make a very objective comparison of results using different implementation of TPV with a use case, no, with a common use case. It is difficult to know which one can be adapted better to which situations. But yeah, personally, in my case, I found it easier to get a probability value based on feedback from the environment. So I found in the literature that making a mapping of Bayesian inference is an easy way to do that now. So I think that the LOIC's implementation can consider another things that, for example, the BDI and other things, and of course it has another properties, but it's difficult to know what are the specific differences or the specific cases that we can be applying in each of the implementations.
So it is a challenge. Challenge accepted, maybe. So thank you very much for each one of you for your presentation, and we have to move probably to the next session that is still social dynamics, but now it is chaired by Alexi, probably.
Thank you very much.
There.
Thank you.
Yeah.
Thank you.
I'm here.
I don't see you. I see you. It's quite late for you.
Well, actually, yeah, it's quite late. Actually, it's the night here. So yes, I'm very happy to moderate the second session on social dynamics. So we will have 3 presentations. One on the land use agent-based model incorporating procedural utility by Yahya Gamal. Another one by Damien Savant, and one by Nicolas Ayoub. Actually, the one by Nicolas Ayoub will be the second one. So Yahya Gamal, are you ready? Are you here first and second ready? Yeah, okay, cool.
I'll share my screen.
All right, so you have 20 minutes to present your work, okay?
Yeah, perfect. Just give me a second, then.
No problem.
Yeah, can you see my screen now? Can you see my screen now? Yeah, perfect. Yeah, so I'll start off. I'm Yahya Gamal. I'll be presenting today a land use agent-based model incorporating procedural utility. This is part of my PhD at the University of Manchester. So to start off, I'll just give an introduction for the rationale of why I'm looking into procedural utility to begin with. I'll go briefly into utility theories, just to give a highlight, and then I'll introduce the agent-based model. And then I'll highlight some differences since I applied the same model on Gama and MATLAB. And if time serves me, I'll showcase a case study where I apply the same model on a case study in Greater Cairo using a GIS data set. And if it doesn't serve me, I'll just jump into the summary and limitations. So to begin with, the rationale behind this model is that I'm quite interested in the global South context with its formal and informal settlements. And when I look into these settlements, not only the spatial characteristics that actually interest me, rather the different procedures to acquire the land plots or the residential units in these settlements is quite interesting in itself. So I really question whether when individuals are migrating between those different settlements, how they compare the different procedures through which they acquire the land and make decisions based on these procedures. So in a way, I'm looking into the effect of market procedures on the relocation decisions. Since I'm looking into decisions and I'm moving forward with a quantitative approach to land use change, I'm focusing on utility theories as they're one of the more commonly used approaches to look into decision making. So basically what I'll be introducing is an agent-based model that allows agents to compare between these procedures when they're making decisions. So within utility theories, I just need to highlight that I'm making quite a distinction between what I label as output utility, which is a traditional approach to utility, mainly applied in agent-based models. Utility is a description of usefulness. Land plot attributes, usually physical ones, are looked into as some form of benefit gained from a commodity, and they are basically used to dictate how agents make decisions or individuals make decisions. Whereas when I'm trying to push into the agent-based model or import into my agent-based model is a concept that comes from behavioral economics that is labeled as procedural utility. It's quite different since it comes from a psychological domain and an economical domain. So it basically focuses on the process of reaching an end goal rather than the commodity or the end goal in itself. It borrows from the psychological domain this concept of well-being due to the satisfaction of the three innate needs. So basically what Frey mentions when he introduces procedural utility is that if an individual undergoes a process and they feel that their actions are causal or that they are connected to others or that they are capable and effective, then they are achieving higher procedural utilities. And he reflected on that going to markets, which is quite the focus here, that fair procedures and fair price setting mechanisms lead to autonomy and competence when undergoing these markets, which makes them more preferable and lead to achieving higher procedural utility. So basically the challenge here, and what I will be moving on to with this presentation, is to quantify these preferences towards markets and import them into an agent-based model incorporating the traditional output utility. And to do that, since Frey didn't really mention how to quantify this procedural utility, as I go back to the original theory where they introduced the three innate needs, which is quite central to his discussions. Basically, this is the organismic integration theory. So what they look into is that reality is an external environment with a set of contextual factors that's shown here. These can be some economical factors, such as markets. And there's an internal self that has some innate needs that can be satisfied, which I previously mentioned. But they do observe these through motivations quantitatively, which I will be importing into the model, where motivations will be used as an indicator of the procedural utility. And conveniently, this theory introduced 4 different regulation categories on a continuum scale, shown down here, where they basically hypothesized that an external environment can be regulated into different sets of motivations according to the type of motivation. So if an individual undergoes a process for material benefit or for avoiding the guilt, then it's more of an extrinsic regulation and has lower procedural utility values. Whereas if an individual undergoes a process for its alignment with one's moral values or an enjoyment of the process itself, for instance, if a market aligns with one's fairness values, then it leads to higher procedural utility. And to observe these, they looked into stated preferences, where they introduced a set of questionnaires, and they asked individuals specifically why they would undergo a specific process, which will be a market in the case of the model I'm introducing. And they provide a set of answers based on previous interviews, and each answer aligns with one of the mentioned motivational categories. individuals and participants just scaled those on values from 0 to 4. So based on that, I'm kind of mathematically formulating this utility as an aggregation of these 4 motivational values. And for the sake of time, I'll just be going forward, skipping a little bit in this, just to highlight that we have 4 motivational values that are aggregated with 2 different sets of factors. The first set assures that we follow the allocated continuum scale that the theory introduced, and the second set assures that the highest observed motivation has the highest mathematical effect in the formula. And the issue here is, even after aggregating these motivations, they do not really compare to the traditional output utility when calculating it based on the land plot attributes. So we introduce a transformation factor beta here, and this is quite centric to this model because we will be applying a sensitivity analysis based on that model, as it represents the weight of procedural utility in comparison to output utility. And to sort of clarify that, I'll just give a very brief sort of example where we have 2 different plots, A and B, in 2 different markets, 1 and 2. Land plot A happens to have higher attributes, so it's more preferable, whereas land plot B has less, but land plot A is in a much less preferred market from an individual's perspective. So the beta factor just assures that in case an individual is indifferent between these 2 plots, then the differences between the benefit gained from the physical attributes should be equal to the difference between the benefit gained from the market procedures. In a way, so the beta just assures that these 2 values end up being equal to be on the same scale and be comparable in the model. So based on this formulation, I'll be introducing an exploratory agent-based model. Basically, what I'm doing here is it's to explore the effect of procedural utility at different procedural utility weights, not based on empirical observations in this specific model. So we have a context of patches that are allocated in different markets, hypothetically could be formal and informal markets, but we're not specifically modeling the process of exchange here. Rather, we're in this specific model, in the Cairo model, we did extend beyond that. But agents generally have random preferences towards the attributes of patches and random preferences towards the markets. So they end up preferring one of either 2 markets, and they're represented here as well with different colors and shades, where markets are in shades of green and agents are in shades of red and yellow according to their market preference. So in terms of the agent's behavior, it's a simple model where agents have a defined neighborhood in a given radius, and they initially explore the system. So they have a bounded rationality within that neighborhood. They explore a preset number of pixels to have a utility threshold that they should exceed. And then after that, they start making the relocation, and it's a satisficing model where at the first instance, and the individual, the agent finds a pixel that exceeds to the threshold that they calculated, they make the relocation choice. So each step represents a year, and agent's age each year. They have a preset death age, and they can breed new agents with the same properties. And at some point during the lifetime, they have to relocate once. So in terms of mathematical representation, I'll not go through this again, but just to clarify, the utility is a linear sum between output utility and procedural utility. We do calculate output utility based on the literature and most of the commonly applied approaches to it. We apply a linear formula that includes the utility per attribute here and the preference towards each physical attributes. And each utility per attribute is a normalization on a logarithmic scale of each attribute according to the maximum in the model. This is commonly a common approach to applying utility in most agent-based models, and we do use this for comparability in case we need to do so with other models. So in terms of measuring output of the model, what I do measure is the satisfaction and segregation. Because this model actually tries to explore whether agents will be segregated in the system according to their satisfaction of markets or not. So satisfaction is a representation of whether an agent occupies a plot in the preferred market or not, whereas segregation follows Schelling's approach, where in a more neighborhood, if an agent is surrounded by 4 or more agents, that prefer the same market that they do, then they are segregated. If it's below that threshold, then they are segregated. So we do apply an experiment here. So I'm only introducing a simplified experiment without going into prices, but we did apply this model with looking into prices in different market types. So the procedural utility weight that I previously mentioned, we do change it from a range from 0 to 1 at increments of 0.1 for a sensitivity analysis, and we apply for each increment to apply 10 runs and take the average for a total of 110 runs. The model is run for 50 years to give at least the agents one cycle of relocation during the lifetime. And we do introduce 10 immigrant agents per year. So to have a sort of representation of how the model runs and what kind of qualitative or at least visual representation we have is on the left-hand side, I'm showing a run without considering procedural utility at all at a weight of 0, whereas on the right-hand side, it fully considers this utility. And what we do find is that we do observe clusters of agents in the markets that they prefer, which is quite interesting because agents are actually looking into the system randomly without really targeting the markets that they prefer, but due to their preferences, they end up making more successful relocations in the markets that they prefer. This is more visible here where the lower procedural utility weight runs have less satisfied agents and the higher runs have higher satisfaction. Similarly shown here through the graph where higher satisfaction rates are shown at higher procedural utility weights. And also we observe lower segregation rates at higher procedural utility weights, which does align with the visual results that we saw as when agents cluster in the markets that they prefer, they are less likely to be segregated as they are mostly surrounded by agents preferring the same market that they do. And interestingly, in terms of the attractiveness of the system, having higher procedural utility weights led to a more attractive system and less immigrants. And this goes back to the fact that we're not considering procedural utility at all. Some plots are really have really low physical attributes, and agents are very likely to fail in relocating to these models. But when agents do take into consideration the preferences towards the market, this might overshadow these low attribute values and end up with higher success rates. So one thing that we wanted to point out is within applying the model in Gama and in NetLogo, the only difference that we sort of went into is the different randomness in generating the initial context that we have. So to clarify, what we go through is in both platforms is we assign market to randomly to an input number of patches, and then we eliminate the isolated patches to make clusters, and we go through this process 4 times, and then to assure that we have a 50% representation of each market, we start assigning the less market randomly to some patches. And NetLogo ends up with clusters without really needing to assign this last step in many runs, which leads to this different representation. And this leads to some differences in the results as well, probably due to path dependence in a way, where higher segregation rates in Gama are observed probably because there are more dispersed patches, and we observe more satisfied agents in market 2. Similarly, because what we did observe is since agents are confined with their bounded rationality, in a lot of cases in NetLogo, they end up having not having the option to really search an area that includes the markets that they prefer, because markets are clustered and not really dispersed. So more success rates for market 2 comes from that specifically. And to sort of briefly introduce the case of Greater Cairo, as I'm running out of time here. Just to clarify, we did apply it both, and there are clearly stark differences between applying this in the 2 platforms, as Gama has the capability to look into vector files, whereas NetLogo doesn't. But this is still a work in progress. But the rationale is the aggregation in NetLogo does lead to different observations and results when running the model in comparison to applying it in a vector model, just because of the aggregation and more representation of service pixels, which are much smaller in the file. So to wrap up, I'm just giving the summary and highlighting some limitations of the approach I've introduced. So this is limited to stated preferences at this point, where the observations towards market preferences are based on questionnaires. We did apply it in Greater Cairo, and we did have observations of market preferences and procedural utility weights ranging from 0 to 0.6, which does have an effect on land use change, but still it's stated preferences. And this utility is mainly more relevant in cases where there are fundamental differences between the procedures of land exchange, mostly in the global south, where we have these formal and informal processes that are quite different, and maybe at this point relevant to look into the preferences toward these procedures in these cases. And also one more important thing to highlight, that we imply that submarkets should be defined based on procedures, which is not common in the literature, where they're mostly analyzed and subdivided based on prices and immigration. Again, this may be more relevant in contexts where procedures does play a role, and there are quite obvious differences between land exchange processes. And finally, just for the Gama and Net logo, it's just to highlight that the randomness is one thing to take into consideration when applying the same model on both platforms, as path dependence may lead to some differences in the results. And with this, I wrap up, and thank you very much for listening. Thank you.
Yeah, thanks a lot. Thanks a lot. You were actually quite on time, so no problem on this side. And thank you very much for this interesting comparison between Gama and NetLogo as well, and that can lead to interesting discussions also on the comparison between platforms. So we move on with the next speaker, Nicolas Ayoub. Are you ready? I see you're here. You're ready.
Yes.
And can we? Yeah, and we can hear you, so it's perfect.
Perfect.
So now you just have to share your slide, and it will be heaven.
Okay. Give me 1 second.
Mm-hmm.
Let me know if you're able to see my screen.
I see for the moment a black screen. Yeah, okay. We have it. It's okay.
Okay. Okay, but wait. Okay. Wait, because it's not responding. Sorry. Let's start over. Okay. Hi, everyone. Thank you. Is it working, Alexei? Is it okay?
Yeah, it is.
Okay, perfect. Thank you. So my name is Nicholas. I'm a former researcher at the MIT Media Lab in the City Science Group. I'm very happy and honored that to be here and to have Alexei chair this session with us. So I'm going to talk about a project called Proximics. It's about the influence of investigating the influence of spatial configuration on human collaboration through agent-based modeling and visualization. This work was done in collaboration with Christian Jara Figueroa, with Arnaud Grignard, and Kent Larson. So at first, we were interested in understanding how people collaborate at the Media Lab. I'll explain a bit more context around the lab in a couple of slides. But given the nature of the lab having a lot of different disciplines, it's interesting to see how people can meet and collaborate in space. And so we were first looking at what is known in the fields of communication and management as the Allen curve, developed by Professor Thomas Allen at the Sloan School of Management at MIT. And he inferred a relationship between physical distance and the likelihood of communicating, which is even now a bit more interesting also given the current reality that we're living. And so if the closer you are physically to someone, the most likely you are to collaborate with that person. And There's also interesting research that shows that if you're in the same building but using different toilets, you will also not be likely to see each other and thus to communicate with each other and consequently to collaborate with each other. We were also looking at the work of Edward T. Hall, the American anthropologist, and he developed the concept of proxemics, where we sort of borrowed a little bit the name. And so Hall's concept of proxemics considers the human uses of space within the context of culture and how their implications relate to cross-cultural communication and the design of the built environment. And so he defined different areas of in space for which you consider different types of interactions, whether it's intimate and you're very close to the person, personal, social, or public. So from there, what we were interested in understanding is how can we model people behavior to understand this concept of proxemics in relation to collaboration. And so the objective was to model the relationship between space and behavior in collaboration processes. So just as a bit of background in regards to the Media Lab at MIT, it's a research facility with 800 people, researchers, staff, students, principal investigators, affiliates, and visitors. So it's sort of a diverse pool of people that work on very diverse types of problems, from urbanism to education or biology, prosthetics and sensing, and so on. And I'm also going to talk briefly about the building, which is an interest to us since it was our case study. So there's two buildings. One is the original building that you can see on the left of this picture, which was finished in the 80s and done by a famous architect, I.M. Pei. And then the second one was done by a Japanese architect a bit later in the early 2000s. And so it's interesting to see how the space has been distributed between groups, and that's a little bit what we wanted to see through our tool as well. So there was mainly two areas that we focused on for this. On one hand, it was about visualizing, so more on the graph analysis side and understanding what exactly is the grand truth. And on the other side, it was trying to simulate to see if we could get to a point where we get close enough to the grand truth. So in terms of process, we started extracting the data from all the people that have been at the lab since 2014. And so we have good records of their position, their title, the groups they were in, and they have a specific username so that we can also infer projects data that comes after. And so we have also people that have left the lab, so not only people that are currently there. So we were comparing also this with the projects data. So the Media Lab is funded in a way that they also have member companies. And so twice a year, there's a members event where the researchers present the work that they've been doing, and they update the database of projects with the projects that they're currently working on or the projects that they want to publish on the website. So what's interesting with the data that we have here is that one, it's self-reported by the researchers, and two, it also talks about projects that are in progress and not only completed projects, and also projects that failed. So that's interesting to note in regards to like the specificity of the data that we were using. From there, we were interested in identifying collaboration through indicators of centrality. So we were running some graph analysis on understanding who is working with who within their own group and within the lab as a whole, so like other groups as well, and measuring the influence of each person understanding who are sort of the leading collaborators between each groups and that break down barriers that act as a bridge between other groups. And then to prepare for the ABM model, we were interested in gathering physical spatial data. So we got the PDF plans of the buildings of the Media Lab, so E14 and E15, which we redrew on a CAD software and combined together. And then that we labeled specifically for Gama, so that we were able to connect the data from the people. So knowing from the data and the people's data, we have the information of which room they're working in. And so we can link them directly to their specific room in the simulation. And so in Gama, we combine the DXF vector plans with the JSON of the project's data, and then the CSV files of the people data. And so now is the time to create a basic behavior that we would give to the agents. And so we came up with the WCBL model, which is the work, coffee, bathroom, lunch. And we divided it into staff and then students. So staff are working, and students are, since they're research associates as well, research assistants, they're also working and studying. So leaving the building more often than their staff counterparts. And so we were applying the behavior to the agents. So as you can see, they were becoming from elevators primary, which was the main elevators of the building, and then they would go at some point they would go to their office, and then they would go on a coffee break into the coffee room, etc., go to a bathroom break, and so on. And so here we can see, so this is Kent Larson, the PI of our lab, and you can see that he's in his office, so things seems to be quite connected. And so here's the first output that we had from the simulation. So in white, you can see the real graph. So based on what we know, who has collaborated with whom, we're able to connect the dots literally. And then we have in yellow the simulated graph, which gives us an idea of, like, depending on the distance and where the agents walk into the building, how likely are they to collaborate together, and so how do we define those relationships? So here's the short video that we made. So we were focusing on those 4 types of people that exist in the lab, and then we were representing it as a line graph with the collaboration. So we focused on the 3rd floor, where it's one of the major floors of the lab, given that there's an atrium there and there's the coffee machine there, and so that it's a place where a lot of people go through. And so you can see with the simulated graph now with Gama, how it is actually quite close to the grand truth, except for a few interactions that are far away from groups that are far away on the floor plan. And so in regards to the results, if you look at here, the ABM is on the A graph. The ABM is the orange line. I hope no one's colorblind, because I don't know if the contrast is good enough. But so what we have here is that on A, the dark blue is if you're from the same group. So the likelihood of you collaborating is obviously the highest. And then we have the cyan color, which is the overlap time, So how long have you been at the same time as another person in the lab? And the orange is the gamma simulation. And so on B, what's interesting is that you can see that we have the model 1, which is the cyan color, is only with the overlap time and overlap time and same group, sorry. And then the model 2, the dark blue, is simply with same group. So you can see that in model 3, which adds all 3 variants, including the ABM, that the ABM actually makes the model better. So even with a very simple behavior, it allows us to predict with more precision if someone is likely to collaborate or not by introducing the spatial component. So this was the work that we did a while back, and since then we're also investigating other explorations around refining this project. So on one hand, there's the spatial configuration. So groups are known to have moved around since the inception of the lab, and the position of a group is dependent on availability of space and size of the group. So in other words, it can be quite random, but it has effects on how people and groups interact with each other and collaborate with each other ultimately. So it would be interesting to develop a model where we can try to change the location of groups, rooms, and furniture. Sorry, and see what comes out of it. And on the other side, it would be interesting to see how we can refine the behavior of the agents, because as I mentioned before, they had a very basic behavior. But modeling people's behavior is obviously extremely complex, and it's not something that we've been able to do so far. And next was explorations around COVID-19. So this was one of the first way we were thinking of understanding how humans are spreading the virus within the space, and so human to human or human to objects that we later refine into droplets, fomite, and aerosols. And so this is a project that we developed with the University of Guadalajara in Mexico by using the concept of proxemics, but sort of reverse engineering it in a way, since in the original intent was to bring people together, and in this case, because of the pandemic, it's to push people away so that they don't get sick. And so we explored the different array of scenarios, whether they wear a mask, whether they social distance, or whether we're ventilating the rooms, or whether we don't do anything. And so you can see how masks are actually very efficient, more so than social distancing or than ventilating. And so we did this on several sites of the campus, and it was good. And so to finish, some of the questions that are raised by this and are relevant to the architecture world is how can we develop better tools for generative design in relation to the behavior of people. There's starting to be more data and simulation in architectural design, but not so much at the architectural level, but more so at the urban level. And so it's interesting to kickstart this sort of research to develop more of an architectural design with the behavioral component. And this could lead to optimizing architectural form finding or the future outcome, and also assist in interior layouts of furniture, workstations, and so on. So yeah, thank you.
Okay, thank you very much for this very clear presentation. So we'll move on to the next speaker, and then we'll take questions for the three speakers. I see there are already questions in the chat. Please, if you have questions for the presenters, write them down so that we don't forget them and you don't forget them as well. So Damien, you're the next one with social influences on consumption choices in university catering. So please, you have 10 minutes to present your work.
Okay, can you hear me?
Yes, and we see your slides as well.
But
so
this
perfect.
isn't in a presentator mode. I don't. Okay.
No, we see the.
Okay, I think it's okay.
Well, actually, if you don't need the presenter mode, no, it's okay.
It's okay. Okay.
It's right.
Okay. Thank you. So my name is hello everyone. My name is Damien Savéan. I am in my second year of a master's degree in nutrition at AgroParisTech. I'm going to present our work on social influences on consumption choices in a university catering. So this project was initiated by an engineer student in second year at AgroParisTech, and I'm currently taking the next step during my internship. This project is under the responsibility of Nicolas Darcel and with the participation of Patrick Taillandier, Ralou Tomopoulos, and Aurélie Maurice. So at first sight, composing a meal from dishes offered in a buffet menu is an ordinary and trivial task. However, this apparent simplicity hides a complex decision-making problem. Indeed, at the individual level, preferences are taken into account, as well as trade-offs related to price, variety, pleasure, nutritional quality, etc. This difficulty increases if we add the possible interactions between eaters. So as a result, food choices made in the presence of other eaters, such as in collective catering facilities, are a combination of the individual preferences and the numerous social influences. Monitoring the evolution of choices in such context can be seen as studying the evolution of a complex system. Many agents establishing multiple interactions with each other, thus producing a system whose evolution is difficult to predict. The objective of this project was to design and test a multi-agent system to simulate the choices of the individuals choosing their dish in university restaurants in accordance with their individual preferences, but also under the influence of the other eaters they were brought to bump into while choosing their food. At a larger scale, the objective, we aim to identify levers to promote a healthy diet in this kind of restaurant. The simulation of those choices has already been documented, but in their work, the authors witnessed opposite effects to those they had expected. So it reinforces the difficulty to predict the choices. So in this model, each food was assigned a score of nutritional quality as a manner of speaking. This score is built backwards. So high score is bad from a nutritional perspective. Here are a few examples. The sum of the scores of the dishes in the meal, so the starter, the main dish, and the dessert was made to be between 0 and 12. In parallel, we defined several profiles for the agents corresponding to the maximum meal composition score, ranging from super gluten, which has a voracious appetite, a score between 10 and 12 out of 12, and to super healthy, a score between 0 and 2 out of 12. there are more agents in the population with a score around 6 than around 12 or 0, because the supergluten and the super LC status are considered as extremes, and they don't represent they represent a minimal part of the population. For instance, the selected meal has a score of 5 out of 12. So thus, this is rather associated with a normal LC profile. This preference, qualified as a targeted score, could be influenced by seeing others' choices. Each individual tend to conform to the other eaters they encountered. If an agent meets another agent, an influence can be exerted. Their score can be modified in one direction or in the other, according to their nutritional profile or their ability to influence each other. So in this case, LC agents meets gluten agents, and who may have his maximum score, targeted score modified. Consequently, perhaps a jam pancake will be replaced by a yogurt. Sorry. So the number of closed agents is also an important variable. The more people there are in the restaurant, the more the influence is important. Nevertheless, because this work is partly based on a study explaining that the social influences are exerted more on the starters and the dessert than on the main dish, one main dish is assigned to an agent without being able to change it. Moreover, the model ensures that the score changes are not too large. A supergluten cannot have a score corresponding to a LC profile if he is influenced by a LC agent. Finally, the economic influence was not taken into account there. Okay, for this simulation, we work with the French University Collective Catering that gave us the plan of a real university restaurant, which is under construction. They also gave us the real menus that they usually propose in their other university restaurants. You can see the blocks near the walls and in the middle of the space, which contain the different dishes proposed by the restaurant. The first simulations allowed us to observe plausible things, which are at this stage rather expected. For instance, the more people there are in the restaurant, the more the influence is important, as I said previously. Here is a short video that enables to see what the models looks like. The agents enter the restaurant and choose one starter, then one main dish, then one dessert, each represented by a cube on the agent's head. The color of the cube reflects the nutritional quality. The blue circle is an indicator for the vegetarian diet, and the other larger circle represents the area where the influences are effective. It's 2.5 meters around the agents. So you may see a trace behind the agents, which color represents the influence on the choices at a given time. Once they pay their meal, the agents disappear. On the left, you can see the dishes chosen by the agents. So to conclude, we can say that this work is an original approach to study the effect of social influences on the choices of individuals in a crowd situation. Future work will attempt to refine the model for some aspects. We will draw on the other work concerning the social influences in such a way that an agent can influence another agent and can be influenced at the same time. We will create networks according to the strengths of the social ties, friends, colleagues, or at least people the agents are going to eat with. We would like to implement argumentation between agents, which means that in addition to the implicit inferences, we will implement explicit exchanges of information between agents. Finally, we will probably choose to focus on the vegetarian diet versus non-vegetarian diet to get around certain problems and additional rules. Eventually, we would like to describe real-life situations in order to test the hypothesis on how individuals integrate social influences into their food decision-making process, and to see if the model is in line with these observations. With further studies about social influences in collective catering, we could identify levers to promote healthy diet in this kind of restaurant. Thanks for listening.
Okay, thank you very much. So now it's time for questions. So we have had actually a number of questions, and one of them is so the first one actually was asked to Yahya Gamal, I think. And it was about his conclusion regarding the randomness in NetLogo and Gama. So it's a very precise question on this, because you seem to obtain different configurations based on, if I understand well, a different initialization of your environment. So how come you can't make the same initialization in the two platforms?
Yeah, so what I did point out is, since the initialization has some randomness to it, where models are basically asked to randomly introduce market 2 pixels in the system. So our conclusion is that this randomness in a way does change how the final output, visual output that we have from the model does come out. And what I meant by path dependence in that sense is path dependence in how I define it is when we have some minor changes in the model initially, they may lead to some drastic changes in the outputs. So in a way, the different initialization outputs that we had for both models led to some slight differences in the numeric outputs that we have from each model, though we had the same trends where changing the procedural utility weight, or the factor that we have been tweaking with, did have similar trends in terms of decreasing and increasing the segregation and satisfaction rates. So it's more of an issue of just taking into consideration that having an initial randomization in a model may lead to different results at the end. So in a way, that's why we actually run each simulation multiple times to make sure we take into consideration these randomness factors.
Okay, I think it's well, there are two sides to this question, and actually one of them we can probably continue to discuss on Slack about how you did your initial configuration, because it's quite strange that you obtain so different results. The second one is about, and you're right about this, is about the initial configurations, which is always a very, very big problem, especially in social simulation, actually. Because you have to take people at time 0, but it's not time 0 for them. They have a history back, they have interactions, they have a number of things, and it's one of the main problems, for example, of synthetic population generation is precisely this one. Okay, so how to create an individual that just come to the world like this, but just don't come to the world like this, but have a history, agenda, and well, different things. So that's an interesting question, even if for you it's just, I would say, just a random function at some point. But basically, this random function represents a number of things. So there are a question. So we had one comment, I take in order, one comment for Nicolas, by Patrick asking if it would be interesting or not to integrate other factors in the model, such as the personality of people or the existence of prior social relationships. So do you have any comment on this?
Yeah, thank you, Patrick. Yes, so as I mentioned, we had a very simple behavior on the agents. So it would be great to refine the behavioral model and create a more complex one. Also with I think Christian also replied on the chat. You know, incoming students, for example, are a very interesting type of persona that we have in those spaces, since they're the new ones that form a lot of relationships and they're responsible for what he calls the weak links, and those are like the ones that are across disciplines and groups, which are hard to model, and that goes with a lot of different things around the model itself, that we, by refining the interaction, we can have more people go next to each other, and chances of encounters would rise, and that will give us a better idea and static image into how can we predict that their likelihood of two people to collaborate is higher or not.
Yeah, okay. I just have a comment on this. I think it really, for me, it really depends on what kind of lessons you want to draw from your model. Because actually you can add in these kinds of model, and not only proxemics, but other social models. You can add a number of things. You can add emotions, you can add influence, you can add history of people, you can add their personality, as Patrick was saying, etc. But the thing is, at the end of the day, what kind of lessons do you want to draw from it? Do you want to, as you said, to use it for architecture, for example? Okay, in which case, if you add too much details about the people themselves, then you can't generalize anything. Okay, you will obtain maybe a perfect model and be able to recreate a situation, but it won't let you learn anything about how to generalize this kind of activity. So it's always complicated, a kind of compromise or balance to have in a model between all the details you would like to have a very realistic model, and the kind of abstraction you need to carry on if you want to draw lessons from it, and draw lessons that go beyond the. So it's just a general comment. And so, but in any case, very interesting to see the models you're building.
Thank you. No, yeah, I completely agree with you. It's a good point.
Okay, and we have one question by Miriam to Damien. So how is argumentation aimed to gain in precision in the diffusion of the healthy diet? I would think that people do not argue more than it tastes good, not well cooked, no taste.
So in fact, this is a reason why we probably choose to focus on vegetarian diet versus non-vegetarian diet. But maybe, yes, if we continue to focus on the healthy diet, healthy dishes or not, maybe we can implement argumentations about the aspect of the food, or after that, if we implement argumentation, so we can imagine in the when the eaters are at the table, they can talk about if this is a hamburger, for example, maybe maybe to change for, I don't know, salads in the next day. So this is a reason why we probably choose to focus on vegetarian diet to simplify some argumentations processes. So I don't know if I answered the question.
I don't know. Miriam should tell whether or not she's satisfied with your answer. Is she here? Yes, she's here. No, she's fine. Yeah. So are there any other questions to the presenters? I know there have been some discussion in the Slack, but I could not tell exactly. Well, in any case, I think well, this session and the previous one for me were pretty interesting to see that actually we are able now to simulate with agent-based models things that go well beyond the simple interactions we could imagine, I don't know, 5 or 10 years ago, and it's really interesting to see the kind of complexity that you can generate. I was thinking about, for example, the model of Nicolas. It's very simple. I mean, the rules are really simple. The representation of people are really simple, but the environment is complex, as well as the interacting rules, the rules of interaction. So, and it creates a complexity which is well, I'm quite impressed actually by the complexity it can create from almost nothing. I mean, if you look inside the model, well, I don't see there is no work, but it's a very simple model actually.
Yeah, no, it's true, and there's also what is interesting is that for me as an architect originally and designer, there's a big barrier of using computer science or data science or simulation tools, which are not very common, and so it's interesting for us also to work on this at the architectural scale, and there was a lot of technical challenges because of the parsing the files of like CAD files and things like this, which was also an interesting challenge with the work that we did with Arnaud and Christian. So yeah, and yeah, if you look at both graphs, you can see that even with the grand truth, which is the real data that we have from the website, and which is the truth, you can see that the ABM adds a layer of precision, even though, as you said, the model is very sort of scrappy. So yeah.
Yeah, but it's I mean, having simple models, it gives you a chance to have some well, let's say more simpler causal relationships between your inputs and your outputs. So it's always, if you can, I mean, especially in terms of behaviors, if sticking with simple models is probably the way to go when you want to draw causal relationships and understand the feedbacks between the different components of your system. Anyway, I think it's time to finish this session if we don't have any more questions, and I don't think we have. So the next, and thank you very much for your 3 presentations, which were very clear, very easy to follow, and very interesting. So I think the next and probably the last session of the day, yes, will be moderated by Arthur. Arthur, are you still with us?
I'm here. I'm still awake, even if it starts to be late in the town.
Yeah, it's a little bit late, so I'm very happy to give you the floor. I won't go to bed, but I don't have to moderate the session. So please, I let you for almost 1 hour.
For 1 hour for the last session. So thanks you,
Yeah.
Alexis.
Good luck.
So I'm very happy to be there to moderate the last session of that first day of the GamaDays. So that session gonna be about model exploration and calibration. And so we're gonna start right away with a presentation from Romain Royon, who's gonna present us OpenMol and how to use it to make exploration of some Gama models. Romain, are you ready? Okay, you're sharing your screen.
I'm ready. Yeah, my screen
Perfect.
is displayed. It's nice. So I'm really honored to be the first speaker of this session. So I will do a really practical session about how coupling Gama with OpenMol can allow you to explore agent-based model using HPC environments. So as you all know, I guess exploration is a much essential aspect for ABM validation. For different purposes like calibration, sensitivity analysis, propagation of uncertainty, or assessment of robustness of the model, or any other really critical aspect of the modeling. To do that, a generic framework to do that I developed is called OpenMol. So I will quickly introduce that in three aspects. There is 3 key aspects in OpenMol. First, you can embed the models which have not been especially built to be explored with this with OpenMol, which can be in C++, in R, in Scilab, and since recently you can easily embed Gama models. So that's the first part on the top left of the screen. And once you have embedded your model in OpenMol, the second part, which is called provide, let you use innovative exploration model in order to ask a question about your models. And once you have defined your question on your model, you can OpenMol will distribute for you the intensive load that is generated by this exploration method on massively parallel environments such as a cluster or computational grids, whatever the technology is. So that's for OpenMol. For today, I wanted to show you in this presentation a really concrete problem about a Gama model, which I've chosen, which is a predator-prey model. And we will use some post-processing using R to post-process and to try to qualify the dynamics of this model. And we will use that to try to reproduce a pattern, which is, for instance, finding a set of input parameters for the model which generate oscillation of the dynamic of the prey in the predator-prey models. So I assume that you all know this predator-prey model. What we want to do exactly, in a more concrete way, we want to have like this, the Gama box, which is actually the Gama model, which have several inputs, which is the number of prey, the number of predators, and some other parameters like the predator energy, which will be run, and in which we'll have one output, which will be the dynamic of the prey, meaning the number of preys at each time step in the model. We want to provide that to a R script, which will compute some statistical stuff on this dynamic and which will output the number of oscillation, which is in the time series that Gama has computed. And we want to embed that in a optimization algorithm, which is called NSGA2, which is a genetic algorithm, in order to see which inputs of the model maximize the oscillation of the prey dynamic. So here is OpenMol for concrete. It's a web interface of OpenMol, which is a client-server software. And as you see on the left part, you have some files, which is predatorprey.oms. This is your OpenMol script. And your folder, which is called model, which contains your Gama model. So on the right part, you have the script, an editor to write some scripting instruction in order to describe what is your exploration experiment you want to run. So to go into more details about this script, so let's first look at how you will embed your Gama model within this script. So you will use what we call a task. A task is something which is able to run a model, for instance. Here you have now in OpenMOL, since the last version, you have a Gama task. This Gama task takes some parameters. The first parameter is your project directory. The project is the Gama project, which contain all your GAML and your input files. The second parameter is which GAML, which is the path of the GAML file you want to run within this directory. Then you have to provide the name of the experiment you want to run, the number of steps you want to execute, and some frame rate to saying that I want to sample my value in Gama at each time step. If I say frame rate equal to 1. So the Gama experiment, in the Gama experiment, you have like some inputs parameter, which are for instance, the max energy for the prey, and you have some outputs, which are some monitor, which will tell you what is the number of prey at each time step. You will have then to plug those inputs of the Gama model and outputs towards variable in OpenMOL, which will let you then define your design of experiment. So here are 3 OpenMOL variables: the max prey energy, prey max transfer, and prey energy consumption, which are 3 doubles. And then in the Gama task, you see here you have the Gama task. It's the same one as we saw here, but I skipped some part to make it more readable. Then you can specify a set part where you will be able to plug your inputs to the Gama model. Meaning you will, for instance, plug the prey max energy OpenMOL variable, and it will be plugged to the prey max energy variable in Gama. It means that each time before the model will be run, OpenMOL will be able to set some value for those input variable. You have to do the same for outputs. For instance, here I want to get back when the model has been run. I want to get the number of prey, the dynamics. So here I will instantiate a variable in OpenMOL, which is an array of double, and I will set it as an output of the task and set it. Then at the end of the model, I want to get this number of prey output. Here we have to use the name of the label of the monitor. It's a bit weird, but I guess it will be fixed in the next version of. It's due to some limitation of the Gama headlets, which will be fixed in the subsequent version. But then now I have my inputs and my outputs, and I want to use to plug. And after this, the Gama task, I want to have some R script, which will be able to compute the number of oscillations. So I've used the Gama task before, and now I will use R task, and I will. So it's the same syntax. I will use the R task, which I will produce some. I will provide some R script using some library to compute. So set here some inputs and outputs, and this number of prey, which was an output of the Gama task, is now taken as input of this R task, and is provided, is used in the R script, on the last line of the R script. The derivative changes, which is the operation of the dynamic. An optimization methods, which has with Gama, the genome part, which is a variation, some objective, something. But then I want to maximize the number of derivative change. And for evaluation, I will say you have to execute for each evaluation Gama, and then the derivative, which is the R script. And then I have to provide other things, like because it's a stochastic model, I have to use the stochastic version of this optimization algorithm and some termination criteria. To run that on the cluster, you can you have just a few more lines to add. You have the configuration of your cluster to provide. Here it's a cluster managed by Slurm, which is a kind of batch manager, but OpenMOL supports many. So you have some parameter to provide to that. And then you see, after your method, after you have defined your NSGA2 evolution, you can just say on the cluster, and the workload of the different evaluation of the model will be distributed among 500 jobs on the cluster running concurrently at any time. So you will have your result 500 times more faster than on your own laptop. So I was not able, I did run this script, but I was not able to get any oscillation. So I don't know why. Maybe it's my R post-processing or because of the Gama model. I'm not sure yet, but I wasn't able to get any oscillation. So it was a bit deceiving. So some advanced info about what I just presented. So everything is worked using containers, meaning the Gama executable is run into a container as well. In Gama, the default version is 1.8.1, which is the latest version of Gama, but you can also select your own tag or version. And you can also provide your own Gama container for those who need to embed plugins and so on. And it runs on top of Singularity, which is available mostly on all computing environments right nowadays. So to conclude, what you should bring home is that OpenMOL is a really good software for model exploration, and now it loves Gama. And also some useful stuff like the website for OpenMOL, a demo site if you want just to try OpenMOL, just to see by yourself how it looks. If you need some help, you can go to the OpenMOL chat or the OpenMOL forum, which is ask.openmol.org. You can subscribe to the next year Ex Modelo School, which is a one-week school about modeling, about model exploration. And you can also, if you're willing to, you can buy OpenMOL services at this address, companies that we have started to sell model exploration services. So thanks a lot. Okay, it was 10 minutes almost.
Yeah, it was pretty much good. You had some internet connection problems, but
no,
I think it didn't really impact the comprehension of the full workflow. It was on the explanation of the OpenMOL script, but I think like if people have some problems or want to dig it, they will have to go on the documentation anyway, or they can reach you. Thanks a lot, Romain, for your presentation.
Okay, you're welcome.
I think we can continue with the presentation of Damien Vernier, which is going to present us a model about traffic adaptation self-calibration using multi-agent system. Romain, can you turn off your screen sharing? So Damien is going to be able to... Okay, perfect. So now Damien, you should have space to share your screen.
All right, so you should be able to see my screen.
Yeah, okay. So we see your screen, we hear you perfectly. Maybe you can just... Okay, perfect.
Hello everyone, I'm Damien Vernier, a second-year PhD student at IRIT in Toulouse. And today I'm going to present to you a calibration system I'm currently developing during my thesis to self-calibrate models using multi-agent systems. So for a bit of context, so as I said, the idea behind my thesis is to develop a new calibration system to perform online calibration of simulation models. So the idea is that you have, let me take my pointer. You have a data source over here, and your model as a black box. Black box, which means that the calibration system does not know how the model works and has to learn its behavior in order to be able to calibrate it. And the idea is that while the simulation is running, the calibration system will receive outputs from the model and traffic data and has to tune parameter values of this simulation model in order for its behavior to match the data that was observed on the real system. So here, why did I choose Gama to implement all this system? It's very simple, because as it was shown throughout this day, it's very easy to implement models in Gama. So that was the main reason. And why did I choose to experiment on traffic models in particular? Is because one of the main reasons is that they are complex dynamic systems, which means that during the life cycle of the simulation, there may be unpredicted changes to the environment. And the observability is very limited, which means that you cannot have information for every point in the simulation. So now let's zoom a bit on the calibration system. Okay. What? There seems to be a problem. Let me refresh the page. Okay, it's working now. So the calibration system I'm designing, I called CaliCoba, which in English stands for Agent-Based Cooperative Calibration. The idea here is that I use an adaptive multi-agent system that will perform the calibration. So you have on the right here the outputs of the simulation model and the traffic data. Here you have some agents that I call objectives that will compute a distance between the traffic data and the outputs of the model, and that communicate with parameter agents whose job is to set the new parameter values for the simulation model. So the core principles between adaptive multi-agent system is the notion of cooperation and local goal and perceptions. That means that when agents are confronted or faced with a problem, other agents will try to help it to achieve its goal and to overcome the problem it's currently facing. And as in many multi-agent systems, each agent only has a partial view and local view of its environment and has a simple goal. And so the idea here is that no agent knows every information about the model, and that the calibration process will emerge from the interaction and cooperation of all those agents. A quick example here to put it in perspective. So imagine we have, for example, this traffic simulation, and want to calibrate it. So the idea here is we'll see which parameters the model possesses. For example, here we can assume that there are two intervehicular minimum distance and the driver reaction time. And there are two outputs, the traffic density and the mean speed over the whole model, the whole simulation. So here, the idea is to plug the calibration system so that while the simulation is running and data from the real system is coming in, the calibration system's job is to tune these two parameters using the two outputs and their evolution in time. So how did I plug my system into Gama? So the first thing is that CaliCoba over here, I developed it in Java because I felt it was easier for me, as it's a language I knew at the time much better than JML. But I wanted to implement models and experiments within the Gama platform. So I had to define a plugin which acts as an interface between the calibration system and Gama. And how it works is rather simple. When an experiment is launched in Gama, at each simulation cycle, some information about the state of the model is set to the calibration system through the plugin. This data is, for example, all the parameter values, the current parameter values, all the current output values of the model. And when initializing an experiment, when launching an experiment, the definition of the various objectives that can be as simple as a simple difference between the traffic data and an output. Once the calibration system has received all this information, it performs a calibration step. So the agents that I presented you just before interact with each other. And once all the parameter agents have settled on a set of new parameter values, these values are sent back to Gama again through the plugin. In order to ease the interfacing between these two components, the plugin defines custom types and skills, which in turn define a set of actions and a way to simply, very easily define parameters, outputs, and objectives from within the Gama platform. So to conclude what I said, so I presented you a new agent-based calibration approach I called Calicoba. I plugged it in a generic Gama plugin, which means that anyone may use it once it's finished to calibrate virtually any simulation model. As it's still an ongoing work, I had not the occasion yet to perform experiments on actual calibration traffic models, but that's planned for the very near future. Thanks for your attention. If you have any question, you can ask them at the end of the session.
Thank you very much, Samir. It was very interesting. So the questions we're gonna ask you questions at the end of the session, and there is just one presentation left, which is Telina Fletcher, which gonna present. Which gonna talk about multi-agent simulation and analysis of surveillance systems. Talena, are you here? I don't see you. Yeah.
Hello, actually, I am taking over for Talena. This is James Human. Talena had some family emergency, so I'll present for her.
No problem. I hope she's fine.
Yeah.
Okay, so well, you should be able to share your screen.
Okay, great. Yes. Let me go.
And so I'm gonna let you present for, yeah.
All right.
Yeah, okay, it's sharing. Okay, well, you have 20 minutes to make your presentation.
Okay, great, thank you. Yeah, so we are presenting on multi-agent unmanned aerial systems analysis. And I'm James Human with the United States Army Research Lab. I live in Los Angeles, California. And my co-author and the one who actually originally made this presentation, her name is Telina Fletcher. So the purpose of this whole project was and presentation is to discuss the simulation, build and analysis, and then also discuss the outputs from our simulation and batch runs. So the background methodology, simulation, build, execution, and linear regression analysis. And the reason we're looking into this is because the Army is now looking at unmanned aerial systems, and they've gotten so cheap and so prevalent lately that now you can deploy them in swarms at large scale and perhaps heterogeneous mixtures of the different types, and have them work with human operators together in a variety of missions. So that leads to just high complexity in design because there are many numbers and combinations of different asset types and people that you can work together. So I've been looking into multi-agent simulations of how humans and UAVs work together in reconnaissance missions. So at least we can put some of that complexity back on the computer instead of the designer. And what we want is a framework for trade space exploration to understand how different asset mixes impact the reconnaissance performance. And our goals in this performance really are accuracy, timeliness, that's speed, and operational signature, which is stealth, how quiet can you be. And the goal then is to develop an optimization tool to determine the optimal blend of assets that maximizes all of these objectives, which would be object identification while minimizing noise and mission time. And this is just a very general timeline of how we worked. So one was identify the problem, and that was just from discussions with actual soldiers and then anyone else in the military. Collecting data was really a literature search of how humans interact with autonomous systems and also knowledge of how autonomous systems perform in general, and then building the Gama tool and running the Gama tool through a high performance computer. So then my colleague built a design of experiments to set the parameters of the Gama tool or the Gama simulation, where we could change the number of operators or change the number of fixed wing aircraft or quadcopters. After building that design of experiments, then run the actual headless mode simulations through Gama, and develop a Shiny app and do linear regression on the outputs so that we can explore the data that came back to us. And finally, we're in the final stage of documenting and reporting. This is our first presentation to the public on the project, and we're developing a paper as well. So this is to describe how the simulation works. This is the scenario we're trying to capture. So imagine you're in the military, you're a commander, and you're trying to move through some field. So you have people or cargo to move through a field. But before you move through it, you have to identify all of the threats within that field. And to help you, you have a mixed set of autonomous assets like drones you can deploy. You may have fixed wing drones that can fly overhead. These are generally fast, and they have a long battery life. But they usually fly at a higher altitude, and they can pick up threat indicators, things like metal content or heat or smoke, something like that. They can pick that up, but they don't know exactly what it's coming from. It's just an indicator. So it has a high false positive rate. So let's say you've gotten a couple hits on your fixed wing aircraft, then you can send quadcopters in. Those are much more agile, and they can fly lower to the ground, so they can take lower level surveillance and move 360 degrees around the object to take pictures from all sides. You can also use ornithopters. These are a more experimental technology. Ornithopters actually are flapping wing aircraft, so they're drones that fly like a bird. And there aren't many commercial applications of these. There's some university research going on, but we wanted to look at their possibilities of this futuristic technology and how it could help. Their downside is that they're slow and they don't have much of a payload capacity, but the upside is that they're very quiet, and they can be disguised to sound and even sometimes look like natural birds, so they don't draw the same attention that a quadcopter would draw. So they do the same job as the quadcopter. They take lower level surveillance, but they do it much more quietly. And then we also actually simulated the operators. So we have humans in the simulation, and we're trying to simulate their behavior. So we did actually a very deep dive into human factors research of how quickly can they interact with drones, how quickly can they send commands, and at what point do they get overwhelmed. So human factors will also affect the output of the simulation, and they'll get more they'll make more mistakes as they get tired. They'll make more mistakes as they multitask and get overwhelmed. And then again, the speed that they can make decisions may cause bottlenecks in the system for all the other autonomous systems that are relying on them. So all four of these are interacting in various numbers in each simulation. And the goal is to classify the whole field, so do it quickly, that's speed, do it accurately so you're not overwhelming the operator and making mistakes. Be stealthy, which means be quiet. So we're measuring the simulated noise at the ground level. And then low cost, which would just, in our case, mean minimize the number of agents that you use. So if you can do more with fewer autonomous agents, focus on that. Now, to get a little bit more specific on the workflow of the simulation, we would start with a scene. That's some field we want to move through with threats and non-threats in there. You don't know where they are. Here is the fixed wing aircraft that flies overhead at a high altitude, but also a high false positive rate, and it can find those signatures of possible threats, and it marks them at different points and puts that in a database. Then the operator can send the lower level aircraft, the UAV, so the quadcopters or the flapping wings, to each point of interest to fly around and take detailed surveillance. And so then maybe you see, okay, this is actually not a weapon, this is just a police vehicle, or this is just a civilian vehicle or a civilian person, so it's not a threat. And then that image gets sent back to the operators, and the operators then decide, okay, is this a threat or is this a non-threat? I can map out all of the threats in the field, and then I can make a plan for moving through that field. And in Gama, this is what they look like. So the operators, they just look like this little, looks like a board game piece, like from chess. And they have fatigue, they have knowledge from experience, and they have an accuracy and situational awareness that changes over time. Then the points of interest, you could have a weapon here like a tank or just a civilian vehicle. The actual threats are red, and then non-threats are green. The flapping wings are the yellow vehicles, fixed wings are this orange vehicles, and the quadcopters are the purple vehicles. And this is what it looks like. So you can see one simulation run, you have the fixed wings go out first, and every time they go over a point of interest, they'll mark it with a little gray square around it. And so we can see all of the points of interest, but these are not visible to the operators until they're scanned by an unmanned system. So the operators don't know they're there until the fixed wing flies over. But then once it's identified and located, then the quadcopters and the flapping wings, they'll fly out to each point of interest. They'll drop down to a lower altitude, circle around it, and then fly on to the next one after they send images back to the operators. And the operators are back in the corner here. They form different colors based on the mode they're in. So if they're commanding an unmanned system, or if they're analyzing an image, or if they're idle, those are all different colors, just so we can see if they're being used or not during the simulation. And I won't run the whole thing, but yeah, at the end it just runs until every single point of interest is classified. And then the squares around them, that's the operator's decision. So if it's a green square around a green cube, that means they got it right, that they correctly identified a non-threat. A red square around a red cube is correctly identifying a threat. But if they don't match, like down at the bottom, right on the road, that means they got it wrong. So there's an actual threat there, but they didn't recognize it and they labeled it as safe. So that's an error that the operator made. And you can see that there's just a couple of them throughout the simulation. But classifying something as a non-threat is quite a dangerous mistake to make. So we're looking at the implications of that. And what we want to do is then run thousands of these on a high-performance computer and collect data on different sizes. So going from 1 to 10 of quadcopters, or 1 to 10 on the operators. And my colleague did this. She ran it on a Linux-based high-performance computer. She output XML files to do the experimental run. I created the actual simulation for her and set up the hooks for the high performance computer. And then, yeah, she took them and did the design experiments and ran them 360,000 times, I think, on her high performance computer. And we ran a regression, and I think I'm a little long on time, so I won't talk too much of the regression, but basically we just wanted to look at, in a very simple linear way, all these different data, or all these different variables and our output goals as a function of those variables. So you can see that we would essentially just fix two variables. So here we want to fix the number of fixed wings, the number of quadcopters at 6 and 3, and then increase the number of operators and see what's the resulting system performance, just as a linear approximation. And this is a fairly typical curve where it does reach a level at some point. So here at around 6 or 7 operators, the curve flattens out and you don't get much more performance after that. So if you're trying to minimize manpower needs, which most organizations are, at least this type of simulation can show you that you're not going to get anything if you put more than 6 human operators into the system. Those are the kinds of questions we were trying to answer. But the linear regression approach, it oversimplifies the data. So we actually came up with an optimization tool that's more of an expert system. And this does multi-attribute decision making using just simple additive weighting. So this is going to be used by a senior leader or decision maker, where you can input weights for the simulation goals. So how much do you value duration versus noise versus accuracy versus the number of UAVs and operators? And by weighting those different goals, it can dig through all of the high performance computing results and say, these are your top 3 system combinations to meet those goals. So yeah, we did 12,000 different design points, different combinations, and we ran each of those 30 times. And so it will look through all of those results and say, if you want, for example, very high stealth, and you don't care about the number of flapping wing aircraft you have, then it would maximize those because they're the quietest in the system. And you can do trade-offs among all those competing goals. And then do a results comparison just using this optimization tool. So this is just one example result from the optimization tool, where it tells you how you're doing on each goal, accuracy, duration, and noise, and what combination of agents and people you would need to achieve that. And so here, this user probably wanted high speed because it looks like it maximized the number of quadcopters and minimized the number of flapping wing aircraft. And this is just a few more screenshots of the analysis tool that we made, so that just the welcome screen. And then here is where the user would input their weights and their constraints. So we treat the number of operators as a constraint and the number of UAVs as a constraint. So they can just say, okay, I only have 3 people available to me, or I only have 5 robots available to me. And then the goals are treated as weights. So as you maximize different weights on different goals, it will affect the mix that the optimization tool chooses for you. Yeah, so just to summarize, we built a system sizing tool for surveillance systems using Gama, where the submodels are operators, fixed wing UAVs, quadcopters, and flapping wing UAVs. We did a batch run of headless simulations to collect data, which was 360,000 of them on 12,000 different combinations, run on a Linux high performance computer. Summarize the data with regressions first, and then also built this nice user interface and Shiny app where users can add weight preferences on those goals of speed, accuracy, number, and stealth. And then the system will dig through all of the data and results and output its top 3 recommendations. And moving forward, I want to add new mission types. So I want to use Gama and the same approach, but look at something other than surveillance. And also a better stealth model. Right now, it's a bit elementary. We just look at the noise decibel level at the ground and add weighting for the higher decibel levels. But really, there should be thresholds based on objective measures such as human detection or machine detection and things like that. So we want to look into a better stealth model. But this was a good first pass at that. I think that's the end. Yes, that's the end of the prepared remarks. This is my contact information at the bottom left. My email address is down there if anyone has any questions. I've written 2 papers using a very similar model to what I presented here. Those are on the bottom right if anyone's interested. They should be available online, but I'd be happy to share them with anyone as well. So yeah, feel free to reach out with any questions or collaboration opportunities. Otherwise, I'll take questions in the session.
Thank you very much, James. It was very, very interesting. So now we're gonna do the last part of the session, which is the question for the 3 different presentations that we had. I'm gonna start with questions for Romain, if you're still there. And I'm gonna go in the order of people asking questions.
I am.
So I'm scrolling back to it. But there were a first question for you, Romain, which is from Patrick Thaïlandier, which is saying that he don't have access to a grid in his laboratory. And you made a presentation using Slurm and using grid computing. And he's asking if it's possible to use OpenMOL on just computing servers with, for instance, 24 cores. And if there is some other exploration algorithm than the genetic algorithm that we did present in OpenMOL.
I think the answer are yes to both questions, if we want to do short. So you can use OpenMOL in multi-thread on a computer. It is able to distribute your model evaluation or 24 cores without any problem. And if you have access to a remote server in SSH, you can also use it. And now with the work I did with Arthur, you're now able to aggregate several SSH server. If you have a bunch of it, OpenMOL is able to load balance the rudimentary load balance execution between several SSH server you have at your disposal.
And thank you, Romain, for the answer. Damien, there is some questions for you too. So there were first question from Sri Rama asking you if the calibration is for the whole system or just some edges.
Or just some?
For some ages.
I didn't understand your.
So I think he's asking if you try to calibrate the whole system at once, or if you consider some more small area and the edges maybe the road of your traffic model.
Okay. No, it's the whole model at once. As I said in my presentation, the calibration system sees the model as a black box. So by design, it can't calibrate some smaller parts of the model because it doesn't know they even exist. I hope that answered the question.
Yeah, I think that answered that question. And Srirama also asked you about what was the inner row in your presentation. Was in row peak just a representation?
The picture, it's a picture I found on Google Images. I don't know that much, but if I remember correctly, it's I think it's an application built by a company. I don't remember the.
Okay. Srirama is completing on the chat and just that he did use it, and so he wanted to know a bit more on your side. And one last question for you, Damien. from Alexi, who asks you, how does your system compare with other equivalent optimization exploration systems, like the ones built on R or even with OpenMO?
Compare on which aspect? On the architecture or
in general,
performance?
How?
Well, maybe Arthur, I can.
Yeah, please.
Yeah, I can give a little bit of precision. The question is it just another optimization system? Okay, so something that will add up to the existing offer, or do you have in mind to do something else than what is already being done by our algorithm to building experiment plans, or being done in OpenMO when they use machine learning algorithm to explore things?
The goal of my system is not to perform model exploration as in OpenMO, for example. The idea is more on to perform data assimilation. So to integrate data in the simulation in real time or quasi real time, provided you have a data source, be it directly from sensors or from an external database. I don't know yet, but so the goal here is not to in a way optimize parameters in real time in order for the simulation to be as close to the data as possible.
Okay, does the
yeah, okay,
the answer?
Okay.
Perfect. And there is one last question for you, James, coming from Patrick Thaïlandier. A question about the spatial environment. In the simulation, you show the environment seems to be simple without any obstacles. Will it be possible to integrate more complex environment? Will it be, and is it planned to?
Yeah, that's a plan. Yeah, for future work, we do want to add something like mountainous terrain, because that blocks the line of sight of a quadcopter. And we want to be able to add the ability for like trees and buildings to hide things. But then also we need to add the ability for the environment to be dynamic rather than static. So yeah, if you think about in a military setting, people are going to be responding to quadcopters if they see it. If they see anything flying overhead, they're going to be moving. They're going to be hiding. So we need to add that, and we need to add the obstacles for them to disguise themselves and hide behind as well. Yeah, we didn't do that in this iteration. The hardest part for this iteration was coming up with the model for the human operators. Getting into so to put the human operator into Gama, that took all of the literature review of getting that working. And everything else was kind of just the bare minimum to support that human operator model. And now we can focus on making the other things have features added to those as well.
I see. Julius is completing Patrick's question and also asking about integrating dynamic point of interest like moving targets and stuff.
Yes, exactly. Yeah, we do want to. Yeah, we do want to do that. But yeah, just it's a matter of adding features now that the human model is working.
I see. Okay, thank you very much. Does anyone have any more question? Otherwise, I think it's pretty much time, and I can leave the floor to Alexi.
Yeah, I'm here. Just no. Well, actually, thank you very much, guys, for your presentations. These last ones, very interesting, and of course, I so I didn't prepare anything, any speech to close this first day. I just want to say that I've been really impressed by first the diversity of the presentations and the domains and your fields of interest in general. I've been also very impressed by the maturity of all the work presented. That's really impressive to see so many realizations. And as a platform designer, actually, I'm proud to see all of this, and I guess this feeling is shared by all the developers of Gama today. I'm also taking much more seriously, and this is something I said during my presentation, also the responsibility we have towards you, actually. When you're building models, some of you are building models for a living, some of you are building models to obtain a PhD, some for completing some tasks, and actually you rely on it. You rely on this platform, and this is really something important we have to keep in mind when we make changes or when we plan for new releases or new features. It is really something we have to keep in mind, and probably we'll interact with some of you in the near future, okay, about some changes we plan to make. That's it. I won't take very long. Just want to say so thank you for today, and of course we have 2 more days of presentations, discussions. So tomorrow, I think, because I don't have the program here, but tomorrow, yes, it begins at 8:40 in France, okay, with a session on ecology and agriculture moderated by Benoit. So I hope you will all be there, and also have a number of try to gather a number of people to follow on YouTube. I think we had today, so I'm not completely sure of the numbers, but here between 35 and 45 people, and between 20 and 30, I think, on YouTube. So quite an impressive number given the number of papers that were sent. So we have 2 more days. In the meantime, don't forget to use Slack to ask questions or open discussions with some of the presenters. And also we will, so maybe immediately or maybe tomorrow, we'll send to all the presenters a link, linking to a Google form, which allows you, if you wish so, to share your slides, to upload your slides and to share your slides with others. Well, at least with the people who participated today, and we will participate tomorrow and the day after tomorrow. Okay, so it's only if you wish so. There is absolutely nothing mandatory about this. But I think it would be something nice if we can keep some material from these 3 days. So thank you again. Goodbye, everyone. So good night for the ones in the same time slot as I am. And good afternoon for the others, and morning, I don't know exactly. And again, thanks a lot for your very, very interesting presentations. Bye-bye.